everyone, and good morning, and welcome to the second day. Hi everyone, and good morning, and welcome to the second day of the winter school. We're sorry for the delay, and we're about to start with our second talk by Gilad Asherov, talking about oblivious computation. Gilad, please.
Thank you. So I'm going to talk today about oblivious computation. I'm going to talk about the hierarchical construction, but I'm going to start the first hour on oblivious sorts. Okay, so just a recap from what we did yesterday. So we talked about the scenario where we have a secure processor in an untrusted memory, and we said that even if I encrypt my information, the access pattern, which memory locations I'm actually accessing, reveals sensitive information. For instance, suppose that a cloud, I upload all my information, genomic information to the cloud, and I always access some regions that relate to the kidney. So the cloud provider can infer that the patient has some problem with the kidney, not say a heart problem. So we talked also about models of computation. We mentioned the circuits model and the RAM model, and we said that the metrics are a bit different. So in circuits, we care about size and the depth of the computation. In the RAM model, we care about time and the size of the memory. And then we say that there is the oblivious RAM model where we can actually simulate whatever access patterns the RAM program makes. So we mentioned ORAM. So ORAM can be viewed as something, as a machine in between the client program and the external memory. And the ORAM receives read and write addresses according to the logical from the client, and then it translated to many physical accesses to the external memory. Security, we ask that this memory distribution can be simulated, namely the simulator that doesn't receive the addresses of the logical memory, the logical sequence, can actually produce the same physical memory accesses as the ORAM itself. Okay, and we mentioned the state of the art. We mentioned the lower bound saying that you cannot do better than log n, namely, when we compile the program, we're gonna get an overhead of log n, where n is the size of the memory. We talked that there are two techniques, tree-based ORAM and hierarchical ORAM, and the best we can achieve in tree-based ORAM is log square. The best we can achieve in hierarchical ORAM is log n. And we also showed that we talked about the lower bound and the tree-based ORAM construction, and we said that today we are going to focus on the hierarchical construction. We saw also an example on oblivious sort. So we mentioned merge sort, and we say that merge sort is not oblivious. So in merge sort, if I want to merge two arrays, and those are the two arrays, then the access pattern over here reveals like the ordering between the two arrays that I'm coming to merge, versus bubble sort, which is completely oblivious. We don't reveal any information about the ordering, about the inputs that we are working on. Okay, and the rest of this talk of the first hour is going to be on oblivious sorts. And I'm asking what other oblivious sorts are. So we all know about merge sort. Everyone knows about merge sort. We said merge sort is not oblivious. There are three major oblivious sorts that people consider in the literature. Those are Bytonic sort, AKS sort, which is a very famous sorting network that has achieved actually n log n. And there is a zigzag sort that also improved the constants in AKS, different kind of sort, but it has better constants then n log n. And so those are the sorts that we have. It's important to mention that they are much better than just a RAM program. They are even in the circuit model. And bitonic sort is also the most practical when you come to use. It turns out that this factor, these constants are too painful. So it's better to, for many ends, it's better to pay this extra log n than actually going to AKS or zigzag sort. I want to show now another oblivious sort, which is simpler. And we call it a bucket oblivious sort. It achieves a runtime of 6n log n, but it has some error probability, and we also need some client storage. And as opposed to those, the 3 lines over here, it's just in the RAM mode. It's not in the circuit model. So it's really different kind of model. Usually what we do, we take something in the circuit model and emulate it over the RAM. But now I'm saying, instead of actually designing a circuit and then running it on the RAM, let's design an oblivious sort that works directly on the RAM model. So the sort is, we need to think about Z over here as something like polylog in the security parameter. So we get negligible error probability, and the client storage becomes something like polylog. And the runtime is 6n log n. Okay, so how bucket oblivious sort works? The key idea is that if you take your elements and first oblivious permute them, okay, oblivious permute, you run some permutation, completely random permutation, no one sees the permutation, and then you run a non-oblivious sort. What you get is the combination of those two, the composition of those two is actually an oblivious sort. So non-oblivious sort, we have very fast sorts like merge sort, quick sort, whatever you want. Only you really need to do is to start with an oblivious permutation. Now this paradigm of first permuting the inputs and then running something which is non-oblivious is also going to play a very important role in the final construction of Optorama, in different primitives as well. Now we see it in sorting. So bucket oblivious permute, how do we permute? The idea is to take the array and interrupt it as buckets, okay? Each bucket has polylog number of elements. And we are going to assign to each element a random destination bin. And we're going to add a lot of dummy bins. So we're going to add a bin that contains only dummy elements in between those buckets. And what we're going to do, we are going to obliviously send all the elements to their designated bins. Okay, so if I write on this element over here that is supposed to go to the 5th bucket, we are going to propagate it slowly to the 5th bucket. And each element is going to have a destination bucket chosen at random, and the elements will actually, at the end, are going to. And on each bucket, we later are going to permute each bucket independently. Each bucket is small, is something like Z. We can do it in internal memory, not on the server. And what we're going to get is actually a permutation. Now, we have a permutation with some dummy elements. When we're going to apply the non-oblivious sort, all those dummy elements are going to the very end of the array. We are going to give them infinity as their key, and then get rid of them, and we get a sort. Okay, so let's see how we do this propagation obliviously. The idea is that we start, those are the buckets, okay? And what I'm gonna do is in the first, I'm gonna work on 2 buckets at a time. I'm taking 2 buckets, and all the zeros, okay, so each one has a designated key that tells him which bucket I want him to send this element. So I'm going to send the elements according to the most significant bit. I'm going to distribute all the elements in those two buckets according to the most significant bit. If it's 0, all the keys that has 0 are going to the left, all those that have 1 are going to the right, and we are going to complete with dummies on the remainder to actually have full buckets. Okay, so because here we have only dummies, remember that those are only dummies, those are the reals. Okay, so if I have like X elements are supposed to be on 0 and Z minus X, they're supposed to go to the right, we have enough elements, dummy elements, to actually match it and have it exactly the number of elements in a bucket, which is Z. Okay, and then we take the next second bucket, the next pair of buckets, do exactly the same, and distribute according to the most significant bit, and so on. Now, after we did all of those, we are going to take the first one and the third one, and again, we are going to distribute according to, now not the most significant bit, but according to the second most significant bit. Okay, so it's kind of a radic sort, where we take two buckets at a time, distribute them, and this is going to propagate. So here we're going to take the 0 and the 0, and we're going to sort according to the second most significant bit. These two, and again, according to the second most significant bit, and so on in this one. Now all those 4 are sorted according to the two most significant bits, and we're going to take now this one and sort according to the third most significant bit, and so on. Now, the only problem that this might have is when there are too many elements that want to go to the same bucket. However, this is what we call an overflow. However, we can show that each bucket in expectation is half full. So because each bucket in expectation is half full, we are going to have we are not going to have overflows with high probabilities. Okay, so this is a bucket oblivious sort. It's really incomparable to those circuits that I described over here, but for the raw model, it's very good that we can use. Any questions before I proceed?
There are no questions as of now.
Okay. So I'm going to now ask a very fundamental question. Can we do sorting faster than n log n? Okay? I don't care about oblivious or not. Okay, so can we do oblivious sorting faster than n log n? And we know that this is not possible if the sort is a comparison base. Okay, we know that there is a lower bound. Any comparison-based sort is not going to have omega n log n over it. Now, on the other hand, in the raw model, when we talk about non-comparison-based sorts, there are sorts that actually can work faster than n log n. They are not in the comparison-based model. Those are like radic sort and counting sort. Those are faster when the keys that we have are smaller. Radic sort works in order kn, where k is very small. This is faster. In the second model, on the other end, we don't have such results. So radic sort, counting sort, they all make input-dependent memory accesses, and we don't have an equally efficient counterparts in the circuit model. So this leads us to the question of can we go lower than k plus w times n log n circuit size? So let me just explain the parameters. So n is the number of elements, k is the size of each key, and w is the associated payload with each one of the keys. And so the question is, can we go lower than k plus w times n log n? And we know that this cannot be such a sort, even the circuit model, cannot be comparator based. This is the lower bound that we have of n log n. Then this holds even if all we care about is let's try to sort bits, namely our keys are just 1 bit long. We'll just have keys of 0 and keys of 1. That's it. So even in that case, we cannot go smaller than n log n. And there is something called stability. Stability means that if we have two inputs, two keys that are the same in the input array, I want them to be, and this one is before this one, then I want them also to be in the same order in the output array. In that case, we say that the sort is stable. So there is also a lower bound saying that such as sorting cannot be stable. So stable sort requires at least n log n selector gates, muxes, in the indivisible model when we treat each element as an OPEC. And this holds also even if we care about just 1 bit sort. There is another lower bound that assumes the Lilly conjecture. I don't want to go into it, but it says that for general K, you cannot have a sorting circuit that is smaller than K plus W n log n. Okay, and we don't have an unconditional lower bound, so we have either comparison-based, stability, assuming some conjecture. There is no unconditional lower bound. So what I'm going to present now is a sorting circuit. So if the baseline is AKS, it gives you sort in a circuit of size K plus W n log n, we show a sorting circuit that works, that its size is K plus W n times K. Okay, I'm going to ignore some polylog star terms. Okay, very small terms. But as you can see, for small keys, when K is smaller than log n, this is a smaller circuit than AKS. Okay, so it's better and it's smaller for K that is little o of log n. It's indeed worse than n log n for general K, as we saw in the lower bound that I just mentioned. The sort is non-comparison based and it's not stable. Okay, so we actually circumvent all those lower bounds. So in order to get this result, we had to look at the problem that is called tight compaction. So tight compaction is essentially sorting on 1 bit key. Okay, so we have elements. This is the input array. Some of the elements are marked. Those are the blue ones. And we want to move all the marked elements to the beginning of the array. It's just sorting in bits on 1 bit key. Now, it turned out that this problem is very central. It led, first of all, to Optorama. So in order to close the gap and get to optimal construction for Oblivious RAM, the way to achieve this was via this linear time Oblivious compaction. So first of all, we show the linear time algorithm in the RAM model that is Oblivious that computes tight compaction. So you can sort 1 bit keys in order n. And in the circuit model, it also led to a very nice result that shows that we can achieve those linear size circuits for short keys. Okay, this is what I just mentioned about this result. Okay, so tight compaction, it's a very central problem. We can look at it in the RAM model or in the circuit model, and we get very nice results out of this problem. Okay, so tight compaction, again, the problem statement, you have an array of size n, where each element is marked 0 or 1, In the output, all the zeros elements should appear before the one elements, or vice versa, whatever. It's smaller. In the RAM model, this is very, very easy. When I mention here the RAM model and not the Oblivious RAM model. So in the RAM model, you just scan your array. Whenever you see 0, you write it down. Whenever you see 1, you wait. Then you can scan the array again and write down all the ones. Okay? But doing it obliviously is much more difficult. So in the Oblivious RAM model, we can use AKS as a basing point, and get a deterministic construction in n log n. This is an open question back from 95. Lighton and Maswell showed an algorithm that reveals the number of zeros and is randomized. There is another algorithm that runs in n log n. And the same lower bound that I mentioned about stability in the indivisible model actually tells us that if you want to achieve stability, you need to pay n log n. Okay, so the fact that we're going to order n means that we must give up on stability. Okay, so those are the two results. In the circuit model, we have linear size circuit for tight compaction. Specifically, it's n times w, where n is the number of elements that I want to compact. W is the associated payload for each one of the elements. So this means that the input is of size nw, so this is a linear size, times some polylog star n factors. And in the RAM model, we achieve an order n time deterministic algorithm for compacting n balls. Each, I look now as each has its associated payload is the word size of the machine, and I assume here that the word size is order log n. This is the same, supposed to be the same. Okay, and both the circuit and the RAM model, both algorithms are not comparison-based, they are not stable, and they are in the balls and beans model, even though when we compute where to move balls around, we use some bit slicing tricks, which is not exactly in the balls and beans model, but the entire algorithm is considered as balls and beans because when we look at the memory, at the blocks that we move in the memory, those are, we treat them as OPEX. Okay, so next, what I'm going to show next is first I'm going to describe this n log n algorithm that is very simple and it's randomized in the RAM model. Then I'm going to describe the linear size compaction circuit. And I'm just going to mention that in the RAM model, in the Oblivious RAM model, we have an order n construction, which I'm not going to show it in its entirety, but it has some similar ideas as the circuit construction. And this is, again, a good time to stop and take some questions.
There's a question regarding the bucket oblivious sort. Is the permutation and splitting between right and left based on the value of the element?
It's based on, so to each element, we made a new key, like you sample new keys to each one of the elements. And then when you move left or right, it's according to the new key that you just sampled. So it's going to be completely random permutation. And then when you run the non-oblivious sort, this is going to be according to the real values of the elements. Okay?
Okay. We don't have any more questions for now.
Okay. So, so now I'm going to show a simple randomized oblivious type compaction in the RAM model in n log n, log security parameter. And the idea is the following. So this is the input. We have a lot of zeros, a lot of ones, and each one has some associated ball with it. So there is information attached with each one, and you want to move all the zeros to the beginning and all the ones to the end. So the first thing we're going to do is going to interrupt this array as n over z bins of size z each. Z is again polylog in the security parameter. Okay, so I'm going to take the first element says, okay, so those are my bins. The picture is not so great because you need to think of it as a lot of bins of small size. Here is more like a square, but I'm going to have a lot of each one of the bins. I'm going to take my input, divide it into the bins, and then I'm going to random shift cycle each one of the rows. What do I mean by that? I'm going to choose a random separator for each one of the rows, and I'm going to shift the rows according to those separators. So it means that over here, that I'm going to start this row as it's starting from here, from 0, 1, 0, and then 0, 1, 1, 0. And this one, I start this row over here. So I shifted, cycled around my rows. Okay, what is the cost? So the cost is just linear because I just move things around and don't do really anything. Okay, now what we're going to do, we are going to sort each one of the columns independently. Okay, so I have a lot of columns, n over z columns, and I'm going to sort each one of the columns independently using an oblivious sort. The cost, if I use bitonic sort, is on n over z times z log squared z, which is overall in n log security parameter. Okay, so this is what I get after I sorted each bucket or each one of the bins independently. Next, the claim is that with very high probability, with overwhelming probability, there is a mixed stripe of size which is not so big, which is something like log to the 4 times security parameter. So let me explain. After we did this column sorting, we sorted column by column, we're going to end up with all the first rows are going to be zeros, all those on the top are going to be ones, and we're going to have very few rows that actually going to be mixed. They have ones and zeros. And if my bin is of size log to the 6 security parameter, then the ratio is something like the size of my mixed stripe is log to the 4 times security parameter. Okay, what does it give us now? I can copy this array somewhere else, obliviously, and then I can, the number of elements that I have in this mixed stripe is something like n over log squared security parameter. What does it mean? That if I'm going to sort it, it's not going to cost too much because it's n over log n, and therefore I can actually sort it very efficiently, and then I can write it back. So let's see the entire algorithm in one slide. So I interrupt the array as n over z bins of size z each, and then perform some random shift cycle. This is important for actually getting some randomness and showing that there is a mixed stripe. After we do this random shift cycle, we're going to sort each column independently. This is like sorting the bins. Then we're going to identify the mixed stripe, copy it somewhere else. It's a bit tricky how to do it obliviously, but it's not very difficult. And then we're going to sort that mixed stripe and put it back obliviously. And now you can see you got everything tight compaction in time, which is if k is polynomial in n, or the one relate to each other, what you get is an oblivious sort, is oblivious tight compaction in time and log. Okay, So this is already something relatively practical that it can use. But now to shape this additional log n and get something deterministic, we have to work much harder. This is like kind where something more theoretical than practical. Okay, so I want to show now a linear size compaction circuit. Again, not in the raw model, but a circuit. But this is again a good time to stop and take some questions. No questions? Okay. So I'm going to show now.
There's one question. Is there a possible input that results in all rows having either all 0 or all 1?
Yeah, of course. We can get all zeros or all 1. The key idea is that in that case, I will pretend that I'm taking a mixed stripe, copy it somewhere else, sort, and then sort it back. Okay, but if the entire input is just 0 or just 1, then everything is 1.
Okay, so we would get a mixed stripe then.
Okay. Okay, so now I'm starting with linear size compaction circuit. Okay, I want to show you a compaction circuit. And our cost model, what I'm going to talk about, we're going to have, we're gonna count now how many Boolean gates we have in the circuit. And I'm going to have special, so Boolean gates, I don't care if it's an AND, an OR, XOR, whatever, I count it as 1. And we're going to have special gate, which is a selector gate. You can think about it as a MUX, and we call it a W selector gate. It gets 2 inputs. You have some selector, and you select either this one or that one. You can implement that with W Boolean gates, but we treat it as W selector gates and count it differently because we are going to play with W. It's going to be a parameter that we are going to play. Okay, so oblivious tight compaction. Again, the problem statement is that you have an array of size n where each element is marked with either 0 or 1. And the output is all the 0 elements appear before all the 1 elements. So the key idea is to start, this is our array. And what we are going to do, we are going first, just let's count how many zeros we have and how many ones we have. Okay, so in this particular example, we have 1, 2, 3, 4, 5, 6. We have 9 zeros. So if you put a separator after the 9th index, in the output array, all the elements over here are supposed to be 0, and all elements over here are supposed to be 1. Okay? Now, it's more than that. We know that all those that are zeros on the left side, we don't need to touch them. They're already in their place. And all those that are 1 in the right side, they're also already in their actual place. We are happy with where they are. And if we're going to give a color to each one of the elements, on all the ones on the left and all the zeros on the right. So let's color all the ones on the left as 1 and all the zeros on the right as blues. They're exactly the same number of ones on the left and zeros on the right. And all we have to do is to select 1 0 on the left, match it with 1 blue on the right, and swap between the two. Okay, so all we have to do is just swap the elements. One colored between the reds and the blues. Okay, so the way we're going to do it, we're going to look at a bipartite expander graph. So by expander, I mean that if we have a large enough set on the left, the number of neighbors on the right is going to be very large. So if we take, say, n over 200 elements on the left, we're going to get almost half of the elements on the right. So this is a bipartite expander graph. It has order 1 degree. So we know how to build such graphs explicitly with constant degree for each one of the nodes. Okay, so it's going to have n elements, n vertices on the left, n vertices on the right. And we're going to put all our elements, we need to think about it, like we put all our elements on the left. And now the algorithm says that if two elements are colored, they are marked, and they have the same neighbor, then we are going to swap them. Okay? So we can actually, because we have these expanders explicitly, we can do everything in a circuit where those are the wires and we have only order n wires. And for every pair of blue and red, we're going to swap the two elements. How many gates do we need for that? This is n times d squared Boolean gates for actually deciding which elements I'm going to swap. And we have n times d squared W selector gates for the actual swaps themselves. Okay, now d is a constant, is the degree. So this is total NW gates. Good. The claim is after we did this procedure, there are not so many remaining swaps to do. So if we consider those elements, those sets of elements that survived, those are like, let's say, n over 200 blues and n over 200 red that survived this procedure. The set of neighbors must be disjoint, because if they had someone in common, they will not have been survivors. Okay, we will have swap between them. Now, from the expansion property of the graph, we know that for any set of size n over 200, the number of neighbors is very big, is more than n over 2. Okay, so what we got so far, we have some component of the circuit that costs just NW, and it already, solves almost all the problems. It's just, all we have to do is to swap the remaining 1%. Okay, so constant fraction, we already did swap in NW. Now, our second component is going to be what is so-called loose compactor. So if that compaction is the problem where all the elements, I have an array, some of the elements are marked, and I want to move all the marked elements to the beginning, loose compactor is the following problem where we have some array, some very few elements are marked, and I want to have an output array that it's smaller, it's like n over 2, and it contains all the marked elements in the input array. Okay, so I cannot lose the blues elements over here. So the idea is that after we did the loose swap, we don't have so many elements remaining swap to do. We are going to do this loose compaction while getting all those elements that are still survivors in the output array, over here, and then we're just going to recurse. Okay, we get like a smaller problem, and we're again going to have a loose swap, loose compactor, loose swap, loose compactor. It becomes easier and easier. When we come back, those elements are going to be swapped at the very end. When we come back from the recursion, those ones and zeros are going to be swapped, and then we're just going to do reverse of the loose compaction. Okay, we're going to reverse the route of whatever we did in the loose compaction. So again, when I recurse, those are going to be solved, and then all the errors that I did in those loose compactor, I'm going to do in the opposite, the reverse direction, and then this is going to be the output. So let's see everything, the entire circuit for now, in one slide. So we're going to have loose swap is going to swap some of the elements. We're going to remain with something like 1%. Then we're going to have a loose compactor, which is going to preserve all the elements that are actually marked. Then we're going to have recursion. At the end of the recursion, those elements are going to be swapped. Then we're going to reverse route whatever we did in the loose compaction. Okay? But remember that some elements are going to be missed in this loose compaction, those that are not marked. Then we are going to decide which one of the elements to output according to whatever we have in the reverse route and the input of the loose compactor. We're just going to coordinate-wise select between this output array and this input array to the entire thing. And we're going to select all those that are marked are now going to be selected according to the output of the recursion. And all those that are not marked, we're going to select according to the input to loose compactor from the beginning. Okay? So what do we have so far? So I showed you now that if you have a loose compactor, loose swap plus loose compactor, you're going to get tight compact. Okay? So if you have a loose swap, we showed how to implement it in NW. And I'm saying if you have a loose compactor of size NF of n plus NW, I'm going to get a tight compactor of size NF of n plus NW. Okay? The question is, of course, now how to do loose compact. Questions?
Yes, there are a couple of questions. The first one is, doesn't counting the number of zeros and ones leak the number of zeros and ones?
No, we do it in a circuit. Everything's in the circuit. So, first of all, we count the number of zeros and one. But what I told about the separator, it's not really a separator that we do in the algorithm. It's something just for explaining the algorithm. This is the circuit, okay? So I count the number of zeros and one. Actually, the algorithm doesn't count the number of zeros and one. It just does this loose swap. Sorry, it does. It does count. It marks next to each ball whether it needs to be swapped or not, but everything is in the circuit, so it doesn't leak anything.
And is there a uniform way of generating expander graphs, or do you get a non-uniform compaction algorithm?
So I think there is. It's a good question. I think there is. Here we look about circuits. So circuits are, yeah, there is a uniform. There is a uniform, as far as I know.
Okay, that's it.
Okay, so what we got so far, we got a tight compactor of size n f of n plus n down. Okay? Now we need to do this loose compactor. So loose compactor, again, you have an array. Some of the elements are marked, and you want to move all the marked elements to be in the output array, where your output array is much smaller than your input array. Again, the way to do it is to look about bipartite expander graph. And it's going to be constant degree, constant spectral expansion. And we're going to have two stages in this algorithm. First, we're going to find, overall, we have only linear number of edges. What we're going to find on those edges, which edges are going to actually be selected. So we're going to find the matching of, the important thing is that we don't want to lose any one of the colored, of the marked balls on the left. So we're going to, out of all those edges, select few edges that we are actually going to carry the elements on those wires. So you think about it as the output wire. These are the outputs, this is the input, and you want to carry the marked elements to the right. So we're going to compute which destination, which wires we are actually going to route on them. Okay, so finding the edges is going to take us n log n Boolean gates, and then actually routing is going to cost us order n W selector gates. So overall, we get here a loose compactor in time n log n plus n W. Okay, and what is important is that this method is non-comparison based. Okay, it's really something we decide how to move the balls, not according to their value, but just if they are marked or not. Okay, that they have a value. Okay, so how do we find the matching? So this is like finding matching in a graph. So all those that are colored on the left, they're proposed to all their vertices on the right, all their incident vertices on the right. Each vertex on the right will accept only if you got only one proposal, and it's going, otherwise you got more than one proposal, it's going to reject all. And each one, if someone on the left now received accept from one of neighbors, then it's going to choose that neighbor and become non-color. So we can show, using the expander properties, that in each iteration, half of the balls that are colored are not going to be colored in the next iteration. Okay, so after log n, this is going to be resolved. Okay, so the output of this procedure, or we need to think about it as wires, that some wires are going to be are going to get value 1, and those are the edges that that we're going to route an element according to them. And this thing doesn't depend on the payload. I mean, we just care if an element is marked or not marked. We don't care what is the associated payload with each one of those elements. So we can run with something which is independent of W, and this costs n log n Boolean gates, completely independent of W. Next, our marked edges, once we know which are the elements that we want, which are the edges that we want to route on them, this is what we're going to use W selector gates. So this required a linear number of W selector gates, and overall this circuit, this component of the circuit, requires n log n plus nW Boolean gates. Okay, so what do we have so far? We have a loose swab that costs nW. We have loose compactor that we showed in time n log n plus nW. So we got a tight compactor of size n log n plus nW. Okay? This is already better than AKS when W. So in AKS it was NW log n. Now we have n log n plus nW. But I promise something better. I promise something that is just n times W. I want to get rid now of this n log n. Okay, and the key insight is just not to stop over here. So I have one more step, and we're going to shrink the size of the circuit, and this is really, really cool. So I'm going to show you now, if you have a tight compactor of size n log n plus nW, you can actually achieve loose compactor of size n log n plus nW. And the idea is the following. I'm going to take my array. I'm going to divide it to chunks. The chunks are going to be of log n balls. Okay? Remember that each ball is a W bit long. And because I'm looking now on loose compactors, I have very few elements are actually marked. And the idea now is that my payload is of size W log n bit, okay? So because I'm looking at each chunk as one ball, I'm gonna have each ball as size W log n. And I'm gonna mark a ball, a chunk, is going to be marked if it has containing a lot of balls that I want to preserve, and it's going to be dense if it has at most 1/4 of its balls are actually marked. So once I change just the dimension of the problem, I'm going to write now type compaction to move all the dense balls to the beginning, to the front of the array. Now, how much does it cost me? So now my n is n over log n, and my w is w log n. Okay? So when I put n over log n over here, I get order n, and n over log n times w log n, I'm going to get overall nw size cell. So the step one, where I moved on the dense elements to the beginning, this was nw size cell. In the second step, I'm going to compact independently each one of the sparse chunks. Okay, so I have a lot of sparse chunks. Each one of them I'm going to run tight compaction, and I know that each one of them is not more than 1/4 full or marked. So what do I have over here? I have n over log n instances of tight compaction, where each one of them is input of size log n, so my new n is log n, and the ball is w size ball. Okay, so what I get when I evaluate it over here, so I get log n log n plus log n times w. Now I have n over log n of those in parallel, so overall this is n log n plus nw. So what I got is a loose compactor that its size is n log n plus nw. So I started with tight compactor of size n log n plus nw and got a loose compactor of size n log n plus nw. In general, let's generalize what we just did. If I have a tight compactor of size n f of n plus nw, I can get a loose compactor of size n f of n plus nw. And the idea is exactly the same. I'm going to look at chunks of size f of n. Each one has a ball of size w f of n. So now my n is n over f of n, and my w is w f of n. So when I apply it over here, this f of n is going to be canceled. And on this one, my new n is n f of n times w f of n. Again, f of n is going to be canceled. And the step one of moving the dense blocks to the beginning is an n times w cell. Step two, I'm going to do a lot of those tight compactors in parallel on small elements. Now I have n over f of n tight compactions to run on f of n balls of size w bit each. So each chunk was of size f of n with a ball of size w. So when I apply it over here, I get f of n times f of n plus f of n times w. And when I multiply by the number of instances that they do that, then this becomes n. And overall, I get for this entire circuit, it's going to cost me order n f of n plus nw. So what do I got so far? So we started with loose compactor of size n log n plus nw. And we showed, we also showed now that if you have a loose compactor of size n of f of n plus nw, you can get tight compactor of n of f of n plus nw. Moreover, if you have a tight compactor of size n of f of n plus nw, you get a loose compactor of n of f of n plus nw, which essentially says that if I give you a tight compactor of size n of f of n plus nw, you can build from it a tight compactor of size n of f of n plus nw. Okay? And what does it mean? That now we can bootstrap. I can start with a tight compactor of size n log n that I showed you how to do. And from this, you can get the tight compactor of size n log n plus nw. And from this, you can get the tight compactor of size n log n plus nw. And from this, you can get n apply log a times of n plus nw. And you can continue and reduce this log n factor that you have over here. When do we want to stop? We want to stop where these terms become as w, okay? Because this is how much we can do. But we have to be a little bit careful because the constants blow up exponentially. So the right formula is something like that. It's c to the d, because this grows exponentially, times n log, this is the number of time we apply log plus nw, and we are going to stop when w is exactly this term, and you just do the calculation. It turns out that all of this becomes nw, and this thing, when you apply c, the constant, to the d, it becomes poly in something which is log star. Okay, so from this tight compaction circuit, you can actually achieve sorting for short keys. I'm not going to get into the details. Overall, the idea is to do a selection, and then I'm not going to get into the details. And what we get at the very end is actually sorting short keys in a circuit of this size. And my message in this talk is that tight compaction is a very central problem. It led also to linear size circuit, an improvement of a problem that we didn't know anything for almost 40 years. And it also improved, it gets us to oblivious ORAM construction, an optimal ORAM construction. And this step we're going to do in the next hour. So now we're going to have a break. After the break, I'm going to describe how compaction is going to help us to actually achieve this. Questions?
There are no questions.
Okay. So I have some references if anyone is interested, and let's take a break.
Thank you, Gilad. We're now going to take a 15 minutes break.
Okay, thank you.
Thank you. Okay. Hi, everyone, and welcome back to the third session of Oblivious Computation, where Gilad is going to give the next talk. Gilad, please.
Thank you. Okay, so we are going to talk now about optimal construction. So just a recap. We have a secure processor, untrusted memory, and even though the information is encrypted, where I'm accessing reveal sensitive information. For instance, if I'm uploading genomic information of a patient to the cloud, and I always access the same places, then the cloud provider can infer that the patient has some kidney problem and not, say, a heart problem. And Oblivious compiler comes to make those access pattern to hide the access pattern. So we spoke about the lower bound, we spoke about tree-based ORAM yesterday. We also mentioned in the last talk the problem of oblivious sort and oblivious compaction, and we showed, and what we're going to talk now is about the hierarchical paradigm for obtaining ORAM, and in particular we'll go to the log-n construction. Okay, so there exists an ORAM with order log-n overhead, amortized, and then we're going to make it also worst case. It's asymptotically optimal. It matches the two lower bounds that we have. It achieves computational security and matches Larson and Nielsen. And if you replace the PRF with random oracle, you're actually going to achieve statistical security. And the lower bound of Goldach-Ostrovsky also holds if the client has a random oracle. So we're going to match also Goldach-Ostrovsky in this model when it's replaced with random oracle. The setting is that the word size of the machine is log n, where n is the size of the memory, so each word is of size log n. So this is the classical model. Client's memory size is order 1 words. The server is passive, it doesn't like compute or do anything, it's just like a memory. It's on the balls and beans model, namely we are not going to use some encoding or bit slicing techniques on the data itself. There is very large hidden constant in this construction. It comes from the compaction that we saw in the previous talk. And it's based on the hierarchical ORAM paradigm that goes back to Goldach-Ostrovsky. Okay, so what I'm going to show now is a short tutorial of the progression in the hierarchical ORAM. We're starting with the very beginning hierarchical solutions, and then sees the really nice breakthrough of Panorama, but Patel, Persiano, Rakova, and Yeo that came very, very close to the lower bound. The construction achieves log-n, log-log-n, and then I'm going to describe how to shave this additional log-log-n using in Opto1. Okay, so the hierarchical ORAM, the hierarchical paradigm. Goldach-Ostrovsky showed essentially how you can get a primitive, from a primitive that's called non-recurrent hash table, how do you can construct an ORAM. What is a non-recurrent hash table? So it's an hash table, namely, I need to have a primitive, an algorithm that supports two operations. First, I have a build. I get some array in the memory. The array contains pairs of addresses and values. And we have to build that, we have to, do some pre-processing, arrange the information in the memory. This is the build operation. Of course, it has to be oblivious. And then later, I'm going to get queries of the form of a lookup, where I'm going to get an address. And then if the address is actually in the array that was there in initial time, I'm going to return its associated value, and otherwise I'm going to turn a bot. In addition, I also might get lookup of an element that doesn't exist in X, or I'm going to get also dummy lookups, which are just pretend that you look up, okay? And what I have to do is to go to some place in the memory and pretend like I'm looking up without revealing what kind of query I receive. If it's a real lookup, dummy lookup, or an element that exists or doesn't exist, okay? And security, this is going to be non-recurrent. The only guarantee that I'm going to have is that each address is going to be searched and looked up only once. Okay, I'm not going to look up for the same address twice. And overall, I need to support not so many lookups. It's going to be proportional to the size of X. Okay, after I reach that limit, this construction is going to be destroyed. We're going to rebuild it again. So the idea of this construction is let's do balls into bins. We're going to take our elements, and each element we're going to mark on each ball, on each bin, we're going to put that ball. And then using oblivious sorts, we can actually route the elements into the bins obliviously without revealing any information. And we need to pad each bin to its maximal capacity. Thus, we're going to have some dummy balls also introduced along the process. Let's see how to actually do it. So the size of each bin is going to be something like polylog in n. Let's say it's log squared n. And so the number of bins is going to be 2n over log squared. Okay, so this is what is called bin packing. I'm going to take my input array. On each one of the inputs, according to the key, according to the address, I'm going to compute a PRF. I'm going to have a PRF key, and I'm going to assign to each one of the balls a destination bin. I'm going to add a lot of dummy balls also. So I'm going to add to each bin exactly its capacity as dummy balls. And I'm going to assign the first, those balls to the first bin, those to the second bin, and so on. And given all this information, I'm now going to oblivious sort. Now we're going to have collisions. So if we have all the balls that want to go to the first bin are going to be one next to each other in the memory. So you need to think of the memory as looking like that, okay? So all those, on this one I wrote 1 according to PRF, and all those balls I also wrote 1. And whenever I compare in the oblivious sort, I'm going to prefer a real ball over a dummy ball. So the result is going to look something as follows. So I'm going to get all those that are 1, that are written 1, those are 2, those are 3, and so on. Now, what we're going to do, we're going to scan all those bins, and we're going to see all the elements that are overflows. And we're going to mark them as overflows. Okay, we can do that quite easily, just a linear scan. And then with one more oblivious sort, we can remove all those elements that overflowed to the very end, and I got all my elements into the bins. Okay? Now, what's the idea? It's the idea that now I can do lookup very easily. When I need to look up for a ball, a specific ball, I'm going just to visit the bin that it resides. I'm going to compute it according to the PRF, and I'm going to scan that bin. And when I need to look up for dummy, I'm just going to visit a random bin and scan that random bin. Now, security is guaranteed because my promise is that I'm never going to query the same address more than once. Okay? I'm going to query everything at most once. And so it's really easy to simulate build, just oblivious sort. It's oblivious algorithm. It has a simulator. And simulating a lookup, it just doesn't matter if you are looking for a real element, for a dummy element, or an element that exists or doesn't exist. I'm just going to look up for a random bin and scan a random bin. So the cost of build is n log n, and each lookup, I'm going to scan the bin, it's going to be log square. Okay, questions so far?
No questions.
Okay, good. So now given this hash table, we're going to build an ORAM, and the ORAM is just going to be a hierarchy of those hash tables. So we're going to have hash tables of different sizes, of doubling sizes. So we're going to have log n tables. The first table is going to be of size 1, and then the second one is size 2, and so on. And access to the ORAM looks as follows. Each access has, read or write, address, and if it's right, we also have some associated data where we want to update the ORAM. So lookup is going to be as follows. We're going to look up for the address in each one of the tables. If the item found in some table, we're going to pretend to look up in the remaining tables. Okay, so this is why we need lookup of dummies. Then after we found the element, if the operation is read, we're just going to retrieve that element. If it's right, we're going to ignore the found element and use the data that we found that we have to write. Okay? After we did those, we have to rebuild. So what do I do in rebuild? So some of the tables are actually built, some are not. And when I'm coming to write back to ORAM, I'm going to look for the first empty level, and I'm going to rebuild that level from all the previous levels, plus the new element that I just found, I'm going to write it back. Okay, so after this operation, all those are going to be marked empty, and this one is full. When I going to write next, T0 is going to be full, and so on. Okay, so let's just look how run some examples. So let's say that this is my ORAM. This is an address. This is the associated data on that address. Now let's assume that the client wants to read the content of 9, of address 9. So the way it's going to be performed is that I'm going to look up for 9 in the first one. Those levels are empty, I'm not going to access. Now I'm going to look up for 9 over here. Again, it's not going to be found. And only in this level, I'm going to find 9, and I'm going to see that it's BCD. Now I want to write it back, and cannot write it back. So I'm going to write it back to the first level. Now let's assume that the client wants to write the address 25 to the value GRY, okay, with the associated value GRY. So I'm going to access each one of the non-empty tables again. I'm going to look up for 25 over here, look up for 25 here, and here I'm going to find 25, and I'm going to mark it as consumed, and I want to run, and then I'm going to do dummy lookups in the remaining tables, and going to write back lookup on this one. However, this is full, I cannot do it, so I'm going to rebuild level T1 from the new element and from T0. Okay, after some more accesses, this one is going to be full, and then I will have to write to build this one from, I'm going to write this level, and so on. Okay, so what is the cost of this, whatever I showed over here? It's a basic hierarchical ORAM. So we are performing lookup. How much lookup cost? So recall that each access has some lookups, a lookup in each one of the levels, and then there is some maintenance of rebuilding a table from the previous tables. So the lookup operation, I'm going to have log n lookups on different tables, and each one requires roughly log square n according to the solution I showed. So it means that overall I need log cube n cost for just performing the lookup. The rebuild is, let's say I have only n accesses. Actually, I'm going to have much more, usually. So when I come to rebuild level I, I'm going to rebuild level I every 2 to the I accesses. So over the course of n accesses, I'm going to rebuild level I n over 2 to the I times. Each rebuild is an oblivious sort. It costs me 2 to the I times log 2 to the I. It's n log n, okay? So overall, the cost over n accesses of rebuilding is this cost. I can take n over there, the 2 to the I cancels out, log 2 to the I is just I get overall n log square n, and this is over the course of n accesses, which means that per access, the cost of rebuild is something like log square. Okay? Throughout the years, okay, so what I just presented is an ORAM that cost overall log to the log cube. Over the years, there was improvement in the lookup, and essentially, we can, using also secondary hash tables in each one of the beans, or actually having better hash tables in each one of the levels, we can effectively search inside each table while paying only a constant term, plus we need some global stash to the entire structure. So it's effectively order 1 for each one of the levels, plus some log n for searching in all the levels. Anyway, it's the entire time for lookup costs something like order log n. And the rebuild stays log square n, where this extra log n comes from the fact that we do this oblivious sort that costs us n log. And then came Panorama, and with a very beautiful idea. And they say that if you remember our Oblivious, the very first Oblivious sort that I presented today, we say that if I first shuffle the inputs and then I can run something which is non-oblivious, it remains oblivious. So they came up with essentially the same paradigm, and they say that hash table, if I first randomly shuffle all my inputs to the hash table to come to build the hash table, then I can do it much faster. I don't need to pay n log n. I don't need to do it with oblivious sort. We can do it actually with just n log n. Whoa. This already removes, shaves a lot in the build process, and we go down to n log n. However, our problem that it's not really randomly shuffled, like our input is not randomly shuffled. But they said with they had the following observation that all the elements that we didn't visit, so when we come to a table, we rebuild the table all the time, right? Okay, we rebuild this table from those elements. We maybe not visit any one of those elements when we in the lifetime of that table. So they observe that if we didn't visit an element, then in the eye of the adversary, it still has no clue what is in those hash tables, what it has in those tables. Okay, where each element resides. Only after I actually access something and I consumed it, it knows something about where the element was residing. Okay, so the idea is that all the elements that we didn't visit are still randomly shuffled in the eye of the adversary. However, when we come to rebuild the level, we don't just take it the previous level. We have many levels that we need somehow to merge into the new level that we are building. So even though each one of them might be shuffled, it doesn't mean that the concatenation of all of them is also randomly shuffled. So what they showed also how to intersperse two arrays in a procedure that costs roughly the size of the two arrays. Okay? So what it means that if I take in two randomly shuffled arrays, I can intersperse them together very efficiently without really need to, I don't really have to permute the arrays again. I can use the permutation that was done in the very beginning. Okay, so any questions? Can we? You're muted.
Yes, actually there is one question related to hierarchical ORAM. And the question is whether the extra lookups for dummies can help to guarantee constant time in implementations.
Sorry?
The question is if the extra lookups for dummies entries can help to guarantee the constant time of the implementation.
I don't understand the question. So the lookup dummies are necessary for security. So I don't want to reveal in which table I actually found the element. So I'm looking for the real element in each one of the levels. And after I found it, I continue to pretend to look up in the rest of the structure. Okay, so this is why I need a dummy lookup. Okay, so Panorama, two things they did. First, hash table of randomly shuffled inputs. And second, if you take randomly shuffled arrays, you can concatenate them and get a new randomly shuffled array. So in both constructions, they add an extra log n, which we have to shave to get the optimal construction. So Panorama, if this was Goldach and Ostrovsky, non-recurrent hash table gives you an ORAM. Now we are saying you need non-recurrent hash table for shuffled inputs, something which is weaker, plus intersperse, this take into randomly shuffled array and shuffle them together, this gives you the ORAM. Okay, so these are the building blocks that we have now. So let's take a look at intersperse. How does it work? So I have two arrays. Each one of them is randomly shuffled. Okay, so the first array has n0, is of size n1. Think for now they are both 4 elements for simplicity, and the size of the two arrays, the sum of the sizes is n. What I'm going to generate secretly, I'm going to generate an auxiliary array that has exactly n0 zeros and n1 ones. Okay, I can sample such an auxiliary array in the memory obliviously. I just like sample each one of the coordinates one by one. In the beginning, this one is going to be sampled. It's going to be 1 with probability n0, n1 over n, and 0 of probability n0 over n. After I chose, I adjust the probabilities and continue. Okay, so this is secret. Now, I'm going to oblivious route elements from the shuffled arrays according to this auxiliary array. So this auxiliary array tells me that I want here to have 0 from, I want an element from I0, and here it tells me that I want another element from I0, here it tells me I need an element from I1, and so on. Now, I'm claiming that this will give you a randomly shuffled array of the entire concatenation of these two arrays. Why is that? So let's see how many possible outputs we have. How many possibilities we have for generating this auxiliary array? This is something like n0 choose n. Okay, we're going to choose n zeros out of n. It also says where are the ones. Okay, so this is what this is the auxiliary array. And now we are saying this is randomly shuffled. So we need to shuffle now all the blue ones over here. And we also need those are the possible shuffling of the second array. And overall, this gives us n factorial. So we get all possible outputs. Now, the idea is that we don't have to repay for the shuffling of each one of the arrays by itself. We just need to do this oblivious route. We have already, someone already shuffled it for us. We just now need to reroute the elements into the output array. So the challenge is to actually move those elements obliviously, and Panorama showed how to do it in n log log n. I'm now going to show you how to do it in order n, and the key building block is compaction. How this is going to work, so I'm going to take my two arrays, I'm going to generate this random auxiliary array, and then I'm going to run compaction on this auxiliary array. What I'm going to get, tight compaction, is I'm going to get all the zeros in the beginning and all the ones at the end. Our tight compaction was in the balls and beans model. It means that at the end of the day, it just moves balls around. It makes some calculations where to move the balls, which balls to move, but it does some computation. But at the end, it's just order n time and order n move balls operation. We can remember all the move balls that it did during the construction, during its lifetime. And then we're going to put our two arrays at the output and perform exactly the same move balls, but in the reverse direction. We're going to perform the same swaps in the reverse direction, and then we're going to get the output array as we want. Okay, so overall, this is order n, very easy given compaction. Questions?
No questions so far.
Okay, so what is now left is how to rebuild the hash table in linear time. We are now looking at a weaker primitive that suffices, and we assume that the inputs are randomly permuted. So again, we looked at Goldman-Ostrovsky, where we took all our elements. We saw how to do it, how to place the balls into the bins using oblivious sort. This cost n log n. It's too expensive. This log n become another log n. In the final construction, we want to shave this log n. Now, how do we going to shave it? I'm going to give you a guarantee that first, before we started, someone permuted all the elements for us. So the game is as follows. The adversary chooses all the elements that we have. It knows all the balls, okay? But before we start the construction, someone shuffled all the elements, and then we start the construction. Okay, so the adversary knows the balls, he chooses the input. Now someone, for free, shuffled all the inputs, and then we start. So the question is, what happens when X is randomly permuted? Can we just throw the balls into the bins? Okay, so it's randomly permuted. The adversary chose the input. Someone permuted all the input. We don't charge for it. And then I'm asking, can I just throw the balls into the bins in the clear, where the adversary can see which ball resides in each one of the bins? Apparently, there's no problem with that, right? Like, it doesn't know which is this ball. I mean, it doesn't know that it might be this one before the permutation. It doesn't know which ball is where. And I can also simulate that. The simulator can take the build. The build procedure will be just take n balls and throw them randomly into bins, into n over log square n bins of size log square n each. Okay? But even though the build is simulatable, the entire construction is not secure. And why it's not secure? Because the lookups reveal information. So the adversary, it later can do lookups as it wishes. It chooses which elements it's going to look up. If it performs n relookups, the access pattern, or at least the loads that you're going to see, are going to be exactly the same as in the build process. And if it's going to perform a dummy lookup, it's going to be a new balls into bins distribution, new sampling of balls into bins into our bins. Okay, it's going to be completely independent from of the build procedure. So we have here an algorithm that we can simulate the build, we can simulate the lookup, but we care about the joint distribution and not just each one of them independently. Okay, so what are we going to do? So the way we're going to build is as follows. We're going to take our n elements and throw them into the bins. Okay, so first we have the n elements. Someone randomly shuffle the elements for us. And then we're going to throw the elements into the bins according to the PRF key, as previously, while completely revealing the access pattern. Now, we are going to sample an independent secret loads of throwing less balls. It's going to be n minus n over log n into the same bins. But it's going to be secret. I'm not going to reveal it to the adversary. So I'm just going to sample a number, secret loads. Now I'm going to take this structure and make two copies. One copy, I'm going to copy secretly up to the threshold, the secret threshold on the left, and take all the real elements. And above the threshold, I'm going to continue with dummies. And on the right-hand side, I'm going exactly the opposite. I'm going to copy until the threshold with dummies, and then I'm going to write the reals. So just to say how to do it, so I'm going to take a bin. I'm going to scan the bin and write in two other bins at the same time. Until the threshold, I'm going to write on this one a real, on this one dummy. After the threshold, I'm going to write dummy over here and the real element over there. Okay, everything is secret. I still didn't reveal the secret loads. Now overall, the overflow pile, this I'm going to call it the overflow pile. These are the major bins. In the major bins, according to the secret load, I'm going to have n minus n over log n real balls. And here, overall, I have only n over log n real balls in this entire structure. So what I can do now, I can write tight compaction again on this one, remove all the dummies, and get an overflow pile which contains exactly n over log n elements. On this one, I can build now, I can build a structure, a hash table, using oblivious sorts. On this one, on the other end, I have my major bits. Now the claim, how are we going to do a lookup? So to look up, we first are going to search in the overflow pile. If we're going to find the element, then we are going to visit a random bin. If we are not going to find the elements, they are going to visit according to the actual PRF key. Okay? The idea is here that we can actually do a hash table while paying a lot for building this hash table, because it doesn't contain a lot of balls. And here, in the major bins, we threw everything into the major bins in the clear without revealing, without doing oblivious sorts. The question is, why is that secure? So let's take a look at the security argument. So in the build process, what we revealed the raw loads of the entire structure, right? On this entire balls into bins, of n balls into the bins. And then during lookup, we kind of, during the build, we removed some of the elements to the side. And during lookup, we moved some of the elements to the overflow pile. And whatever now real element that is found in the overflow pile, we're going to visit a random bin during lookup. So it's like throwing n minus n log n balls into the bins, and then the remaining n over log n balls, we're going to again throw into the bins independently using fresh randomness. Okay? So overall, it's like throwing n minus n log n real balls into the bins, and then the remaining n over log n again throwing into the bins. We're going to get a completely independent balls into bins loads independent of the build process. Okay, so those two are going to be two independent instances of balls into bins. Any questions?
No questions.
Okay. Okay, so this is the main trick, how we can actually build the hash table in linear time. The idea is that I'm taking all my balls, throw them in the clear. Some balls I'm going to put aside secretly, and then it's kind of hashing them again in the access pattern, while actually it's like obscuring the access pattern later. Okay, so now all is remaining is like showing how to actually search inside each one of the bins. I'm not going to show the entire construction, but we need another trick to actually do it. So we are working in the RAM model where the word size is W, and say that you have n balls, each of size d bits. How much, what is the cost of actually running an oblivious sort on these balls? So if you have really, if your element doesn't reside in one block of the ORAM, you need like several balls. This is the cost of oblivious sort. Okay, it's d over w times n log n. But what if d is much, much, much smaller than w? Particular, if one ball, if one RAM word can contain a lot of balls and not just one, or you don't need more than, it can contain many balls. So the idea is to use packing. We can put d over w over d balls in one memory word. And then we can sort in time. Instead of having the ceiling, we can just remove the ceiling. In time, which is d over w and log square n. Let's say we are using Bytonic sort. And when n and d are small, okay, when n is something like a polylog n, w to the 4, and d is log w, we can sort in time which is linear and not n log n. Okay? So the idea is to do SIMD operation, like single instruction, multiple data, and we can sort, when we pack a lot of elements into one memory word, we can actually sort much more efficiently. Where are we going to use this packing trick? So each level in the ORAM is just a lot of bins. Each element resides in a random bin. The size of each bin is polylog n. And when we have polylog n, the metadata telling where each element is going to be log n, okay? Because if we have something which is just log polylog, then pointers is something like log. And so we can essentially compute on metadata, on pointers, and compute where to place each one of the balls in a packing way, and therefore we can actually shave the log n that comes from this place using this packing trick. So I'm not going to get into the details on this one. I want to say also that this packing trick also comes, I described in the previous talk how to do the oblivious tight compaction in the circuit model. I did not describe how to do it fully in the RAM model, but in the RAM model, we also need to use packing to actually achieve linearity. Okay, so for the last to conclude, I'm going to talk about how to move from amortized complexity to worst case complexity. So what we have, the construction that we had so far, we got a taste of this log n overhead construction in amortized sense. Some operations are longer, they require order n operations. Like if I need to build now the last level in the ORAM, then I need to intersperse all the levels up to that level, and then run the hash table. This is going to cost order n, it's going to introduce delays and so on. What I want to do, I want to have order log n overhead in worst case. So the problem is that classic de-amortization technique of hierarchical ORAM, which goes back to Ostrovsky and Shuk from 97, it's not compatible with the construction of Toptorama and Panorama. Let's see why. So before I even start, I would just want to mention that what I described is the rebuild process where I take all the levels and push them to the last level, or push like levels into many levels into one level. It's a bit not so friendly with de-amortization. Instead, we can look about an alternative procedure which is more friendly, where I just push each level one level down. Okay, so I'm going to push all the elements over here to the next level. I'm going to get half full. This level is going to become half full. I'm going to push this level to the next level, and this level again is going to be half full. And this level was before the procedure half full. I'm going to push it down to the next level, and this one is now going to be full. Remember that this is of size, let's say n. This is of size 2n, but before the procedure, it is half full, so it contains an element. So after the procedure is going to contain 2n elements, and it's actually full. So what we have now is just like we can push down each one of the levels. How does it help us? So we have kind of two procedures. One is where we push down the levels, and one when we push the element and merge. This is when we come to the final one that we actually want to rebuild. We just push it down and merge the two levels. So we have two kind of procedures. One is just push down, compute. You kind of build a new level just from the content of the level above. And in this one, we're going to build it from our level and the level above. What is good about this procedure is it's very friendly for de-amortization. It is slower to rebuild, and therefore it's easier to de-amortize. And moreover, we now don't need to look on the entire structure and pushing it into the last level. We just need to look at the level above, and that's it. Okay, so the de-amortization is going to look at two consecutive levels, and that's it. So how do we de-amortize? Now I'm going to look only at level I. So level I, its lifespan of each one of the levels is it's half full, and then it becomes full, and then we push it to the level below us. It's half full, and then it's full again, half full, full, and so on. Now, I'm now going to look only at level I. At level I, if this is the lifetime, I'm going to build level I already at this point. Okay, I'm going to start the rebuilding of level I already after this level was built. I know exactly what elements I want to rebuild level I from. Okay, so I can start rebuilding level I far in advance. So at this point, I already can start rebuilding level I. At this point, again, I can start rebuilding level I. I know far in advance before the deadline, I know to start to rebuild. I do this process on the background. Every access, I'm doing a little bit of this process. And so when we reach the deadline, when we actually need the new table, the table is already built and ready, and we can use it. What happens when we come to use this deamortization procedure? Okay, so this is the deamortization procedure with classical hierarchical ORAM. What happens when we come to use this deamortization with panorama and optorama? The problem is this randomness reuse technique that we mentioned. So in optorama and panorama, we have security as long as we never reconsume the randomness of that element. So we say, as long as you didn't visit that element, the adversary has no idea what resides in that element, and therefore it's still randomly permuted in the eye of the adversary. So if I want to start rebuilding my table far in advance, while still accommodating lookups in the level above me, it might be that this element, this randomness, is going to be consumed, and this is going to break security. Okay? So the deamortization techniques of Ostrovsky and Shub do not work with panorama and optorama, and the construction is just in amortized sense and not in worst case. So this is the main challenge, is that at this time, when we start rebuilding level I, maybe we are going to look up for 25, and this will mean that the entire security of our hash table is broken. So the main idea to solve this issue is to have 2 copies of each one of the levels. And each level has an active copy and a copy that is being rebuilt. And the idea is that if I'm going to do lookup over here, I'm going to rebuild the other copy. And when this one is being rebuilt, I'm going to use that lookup. So the idea is to have some cascading construction such that when this one is being rebuilt, if I'm going to look up over here, then the randomness over here is going to be reused, but not this one. And so we can adjust and have independent randomness between the 2 copies. It's a little bit, actually how to do it is not so easy, but the overall idea is again to have 2 copies, one I'm using, one I'm being rebuilt, and kind of balance between the 2, so that we never actually reconsume the randomness when we come to rebuild. So that's it. That's what I have. So for conclusions, we saw lower bound, how the lower bound cost of ORAMs are log n. Yesterday, we also saw the tree-based ORAMs of log square n. We also saw some oblivious sorts and some advances in sorting circuits. And now we got a flavor of the computational security and of optorama and panorama, where we can actually achieve log n in worst case. Some references, what I talked about in this talk, for whoever is interested, and that's it. Thank you.
Thank you. There is one question actually related to the implementation. The question is, the asymptotic results look very nice, but do they actually result into improvement in practice? In particular, do you have elements of comparison about the constant cost between the tree-based ORAMs state-of-the-art and the hierarchy-based ORAM state-of-the-art?
No, so the constants are really bad, especially if you want to shave this log n. We saw the previous talk how you can have very nice tight compaction in n log n, and we want to shave this log n. You pay extra factors in we use expanders and stuff that is really costly. I don't know exactly the comparison between the log n and log square n. It's still a work in progress. But we do understand now that theoretical, we know that the theoretical result, we know that the lower bound is tight, and we need to achieve this log n. This is what, this is where we need to push our efforts.
Okay, thank you. We don't have further questions.
Okay, thank you.
Okay, great. Thank you very much. That concludes the oral session and the 3 talks. We'll take a 15 minutes break now, and we'll resume with the next session about vector Ole. Thank you very much.
Thank you.
because this is the step. Hi everyone, and welcome to the next session on vector oblivious linear evaluation, which will be given by Peter Schul. So Peter Schul is an assistant professor in the Cryptography and Security group at Aarhus University in Denmark. He has worked extensively on bridging the theory of secure multi-party computation into practice with more efficient protocols and implementations. He began this line of work while doing his PhD with Nigel Smart in Bristol, where he worked largely on the SPIDS family of protocols for dishonest majority MPC. He's also known for his work on faster protocol for Oblivious Transfer extension, and more recently on homomorphic secret sharing and pseudo-random correlation generators, which is also going to talk here in this call. So we're very, very happy to have Peter here. Peter, the stage is yours.
Thank you very much, Kamid. I just want to say it's a great honor to be part of this school this year. Really happy to be here. So I'm going to talk about vector oblivious linear evaluation. This is the first on 2 of these talks for today. Okay. So to start off with, just a quick overview of the 2 talks and how they connect with the rest of the school. So this talk now is going to be a kind of slightly more gentle introduction to vector OLE and OLE, including some basic protocols and applications to motivate this core primitive. And then the second talk this afternoon will be focused on an application of vector OLE to building efficient zero-knowledge protocols that can scale to handling proofs of very large and complex statements. And then tomorrow and on Wednesday, Yuval and myself will be covering the PCG part of this talk, this school on pseudo-random correlation generators in this series of 4 lectures, which will also be connected to vector OLE, since there we will also cover some silent vector OLE protocols, which have much lower interaction costs than this distinct kind of interaction pattern amongst the parties. So that's an extra tie in there, which will not overlap too much with what's covered today. Okay, so this talk, in a bit more detail, will start off with some basic definitions, covering OLE, vector OLE, and a few useful variants that you often come across when looking at protocols that use these primitives, and then move on to some motivation, including multi-party computation and different kinds of applications like oblivious pseudo-random functions and private set intersection. And then finally, in the second half of the talk, I'll be looking at some basic constructions, including building OLE or vector OLE from Oblivious Transfer or homomorphic encryption, and talk a little bit about how we can add active security to these protocols before wrapping up with some conclusion. Okay, so what is oblivious linear function evaluation, or oblivious linear evaluation for short? So this is a 2-party protocol between a receiver, Alice, and a sender, Bob. And Alice has some input X, which here is just an integer modulo P. You can generally define OLE over any finite field or ring, or even any kind of general finite group if you like. But here let's just focus on integers. And the goal of this protocol is to have Alice and Bob exchange a set of messages, at the end of which Alice will output this value Y, which is a linear function evaluated on her input X, where the linear function is just a pair of elements A and B input by Bob. So intuitively, the security we require is that for the side of Bob, if Bob is corrupt, then he doesn't learn anything about Alice's input. And on the other side, if Alice is corrupt, she doesn't learn anything about Bob's input beyond the output of this linear function. So as is typical in secure party computation protocols, when we define security, we typically talk about an ideal functionality. So you can think of this as a kind of trusted box, which takes as input the private inputs of the 2 parties, evaluates the function, here it computes Y, and just outputs it to Alice. And then when we look at the formal security definitions of 2-party and multi-party computation, then if a protocol is secure, then this definition of security guarantees that for any corrupt party in this protocol, they will not learn anything more than can be deduced by the ideal functionality, which they can interact with here by just giving their inputs and learning the desired output. So in the case of OLE, if we look at this functionality, then one kind of natural weakness, which some people find a bit odd, is that, okay, Alice can just input X to be 0, and then they learn Y equals to B. And then that seemed kind of pointless because half of Bob's input is leaked already. So of course, this is always possible. It's allowed by the functionality. But actually, in pretty much all of the applications of OLE that we look at, Bob's input B usually doesn't really matter that much. In fact, it's almost always just a random value which is sampled independently every time you call an OLE functionality. And one way to illustrate this is a different lens of an OLE functionality, which is viewing this as secret shared multiplication. So here, Alice and Bob only have the inputs X and A, whereas Bob just samples his second input B uniformly at random. Then when Alice obtains the output Y, we can view the pair Y and minus B as an additive secret sharing of the product A times X. So now clearly Alice choosing X equals 0 doesn't help anymore because we know that this product is always going to be 0. So this case where we sample B at random is pretty much the only way that OLE is going to be used in our protocols. And in some cases, when you're building OLE, you can save a little bit of efficiency with that kind of relaxation. So I think for secure party computation especially, this is perhaps a more useful way to view and even define OLE in the lens of multiplication. Okay, so that was OLE. Let me also cover a few important variants of OLE. First off is random OLE, where, unlike on the previous slide where Bob's B was sampled at random, here we're going to have all of the inputs, X, A, and B, sampled at random by the functionality. So there are no private inputs. The parties just receive A, X, Y, and B as outputs. And finally, we want to look at vector OLE, or volley. So here, Alice still has the input X, and Bob this time has an input, a vector of elements A and B, and Alice will obtain this kind of vectorized function applied to her input X, obtaining the vector Y. And just as with OLE, for vector OLE, we can also define a random variant where the vectors and the input X are sampled by the functionality. Okay, so building on from this, I want to show a few basic connections and observations about these functionalities. So firstly, it's kind of obvious. If you have n instances of an OLE functionality, you can use this to build a single vector OLE of length n. So Alice just inputs the same X into each of the OLEs. So this is an unconditional but perfectly secure reduction with passive security. And you can also make this actively secure with a little bit of work. On the other hand, if you want to go the other direction, build vector OLE from, so build independent instances of OLE from vector OLE, then that's kind of impossible to do with just one instance because of this restriction on Alice's input to be a single scalar. So this kind of implies that vector OLE should in some sense be a little easier to build than OLE. And if you look at some protocols, this actually turns out to be true, and that kind of motivates focusing on vector OLE as an important building block on its own. So secondly, if we have a random OLE functionality, then it's known that we can easily convert this to build OLE on chosen inputs from the parties, again with unconditional security. And here the reduction requires a small amount of interaction, where to convert the random inputs, each party essentially one-time pads encrypt their real input with the random OLE inputs, which requires sending these 3 field elements over the network. And so again, the implication of this is that it's enough to just focus on random OLE for applications. And in fact, in the silent category of protocols, which will be talked about tomorrow and Wednesday, that is the main goal which they achieve with much better efficiency. And finally, if we look at OLE on its own, then it's quite easy to see that this implies a 1 out of 2 Oblivious Transfer protocol. So to see this, you can imagine Alice as the receiver in the OLE, also being receiver in an OT protocol, where her input X, she can now just choose to be either 0 or 1, which then kind of flips a switch, allowing her to receive one of 2 messages, which can be defined by Bob's inputs. And so because of known black box impossibility results of constructing Oblivious Transfer from one-way functions or one-way permutations, we kind of know that it seems very likely that public key cryptography is necessary for building OT and therefore also for OLE. So for all of the constructions we'll look at, there will be some kind of public key style techniques involved at some point in the protocol. Okay, so let's move on to some motivation for actually using OLE. Now, you may recognize this slide from one of Alette's talks yesterday. This is on secure computation in the preprocessing model, where the parties ahead of time will maybe run some interactive protocol, or perhaps obtain from a trusted dealer some source of correlated randomness, which can then be used to improve efficiency when they're doing an actual secure computation protocol after the inputs have been defined. So if you have this source of correlated randomness, then the online phase can be much cheaper, information theoretic sometimes, and lightweight computation. So the way OLE and vector OLE come in these protocols is in this preprocessing material. So we can view a random OLE as a kind of correlated randomness, which can be distributed to the parties in advance. And as a simple example here, I'll show how given 2 independent instances of random OLE, Alice and Bob can non-interactively convert these into a multiplication triple. So multiplication triple is used from Beaver's classic protocol for doing secure multiplication in online MPC protocols, common in all kinds of protocols. So viewing OLE as these secret sharings of the product of the inputs A and X, and the second OLE A prime times X prime, we put these in a box to denote the secret shared, then we can define this product of X plus A prime and X prime plus A. If we expand out all of the 4 cross terms here, we see that firstly, X prime is computable by Alice, and A prime is computable by Bob. And then the last 2 terms are exactly the secret shares, AX, A prime, X prime, which we have from the OLEs in the first place. So combining all of this together, we can use this to define a multiplication triple, where the values on the left, X plus A prime and X prime plus A, are already views as secret shares of the random OLE outputs. So this gives us this additive secret sharing of U, V, and W, where W is U times V, and U and V are otherwise random. Remember, this is a non-interactive reduction, so you just need to take the random OLEs and it can immediately define this multiplication triple with 2 parties. So other uses for OLE and vector OLE in multi-party computation protocols can be, firstly, more generalized form of multiplication triples. For instance, if you use vector OLE instead of OLE, you get this scalar vector multiplication very naturally. You can also build this up in batches to perform matrix vector multiplication or matrix triples. And secondly, if you want to go to beyond 2 parties, then you can have n parties run pairwise instances of OLE or vector OLE and build up multiplication triples this way. One caveat here is that now they have to do some interaction to be able to convert the random OLE instances into multiplication triples. And there are also other approaches for generating multiplication triples based on somewhat homomorphic encryption, as used in the early iterations of the Speeds protocol, which give a kind of different flavor in terms of efficiency from using OLE. And finally, one important application of vector OLE is for building authenticated secret sharings of correlated randomness used in the preprocessing phase. So this is a key building block in actively secure protocols for MPC, such as Speeds, where we authenticate secret shared values with information theoretic max. And this is something I'll also be talking about in the second talk later today on zero knowledge from vector OLE. Okay, so I want to talk about another application briefly, which is this time just for vector Ole, and it's for building something called an oblivious pseudorandom function. So a classic pseudorandom function is modeled by this security experiment here, where we have an adversary on the left who is interacting with some oracle, which samples a random bit B and a random key K, and then receives these queries on input X from the adversary, where the oracle will either compute a pseudorandom function F applied on input K and X, or it will sample a random function and output the random function applied to X. And the goal of the adversary is to distinguish between whether the actual function F is used or there's just the random function. And if the adversary can't distinguish, then F is a pseudorandom function. So in an oblivious PRF, we have this two-party protocol where one party, Alice, has the key and Bob has the secret input X. And at the end of the protocol, Bob should learn the PRF evaluated on K and X, whilst not learning any other evaluations of the PRF. So intuitively, you want that the PRF applied to any other input Y not equal to X remains pseudorandom even after the execution of this protocol. So how can we build an oblivious PRF from vector Ole? Essentially, there's a very natural construction where you can take a vector Ole of, say, some length n, and this will give you a batch of oblivious PRF evaluations on n different inputs. So here, Alice, the receiver in the vector Ole, is now going to play the role of the key holder in the OPRF. So then Bob on the right has these inputs AI, which are going to be the inputs to the pseudorandom function, and then these random inputs BI as usual. Then Alice learns the vector Ole outputs, and then we define a pseudorandom function as follows. So first, Alice defines a batch of keys by taking the vector Ole outputs with this random value S and the outputs TI. Note that this is a kind of different but correlated key for each value, for each index I. And then Bob will simply define its output by taking BI, which was its random input to vector Ole, and hashing it with some hash function, say a random oracle. Okay, so this might look a little bit strange because it's not clear that there's actually a pseudorandom function involved here. But if we take a little closer look, we can define the following PRF, which is defined by hashing, so taking a key, which is this pair S and TI, and then input AI, and hashing TI minus AI times S. So obviously this will get the same value which Bob computes on input BI for the input AI. So this is in some sense correct. And to argue that this is also pseudorandom, so consider what happens if Bob wants to learn FKI of some A prime value, which is not equal to AI. So then this is equivalent to trying to predict TI minus A prime times S for this different A prime. And intuitively, because the secret S is uniformly sampled by Alice, then Bob shouldn't be able to guess this. And so by applying the random oracle, this will give a pseudorandom value as the output of the PRF. And actually, you don't need a random oracle for this. You can rely on some variant of correlation robustness for the hash function. But another important thing to note about the definition here is that because of the way we define these keys, which are somehow related for each distinct evaluation of the PRF, this isn't a strict OPRF. It's more it's known as a batch-related key OPRF, which is a slightly different functionality. And one more thing, so there is a bit of additional leakage strictly because Bob doesn't just learn the PRF output, it learns this pre-image BI before applying the hash function. But as I argued before, the remaining PRF outputs are still pseudorandom to Bob, so this isn't a problem. Okay, so what can we use this OPRF for? Okay, actually, one second. Yes, okay, so if we instead use a random vector Ole to build this, where Bob takes this random value Ri, output from the functionality, instead of its input AI, then the natural way to convert this into an OPRF evaluation is to have Bob send this correction factor DI based on its input AI. This then allows Alice to adjust her keys by adding DI times a secret S to define the new set of PRF keys, which again lead to the same correct outputs. The reason we're looking at this like this on this slide right now is that if you have this, say, ideal source of random vector Ole from some preprocessing phase, then the communication here in this protocol is just sending a single field element from Bob to Alice, which is the same length as its input, AI. So this is optimal communication for an OPRF protocol, given the random preprocessing of vector Ole. So that's a really nice thing about this OPRF protocol when you do it in this batch way. Okay, so now let's think a bit about the applications. So one kind of different way of viewing an OPRF is that this is kind of a random 1 out of Q OT, where here Q is the field size or the size of the inputs to the vector Ole, where Bob learns one of these and Alice can compute any of these by applying the hash function in the right way. So this is useful for certain kinds of correlated randomness in MPC protocols, like these masked one-time truth tables that can be used to perform, say, table lookups or other gates more efficiently in the online phase, as was also connected to some parts of the function secret sharing talk from a Let's talk yesterday. So another, I guess, more typical application of OPRFs is to use in things like password authenticated key exchange protocols, like the OPEG protocol. But these protocols actually typically use a DDH-based construction of an OPRF, and well, you could potentially apply some batch thing. I think for the applications they have in mind, it seems less useful to have this very large batch of OPRF evaluations, although it could be that in some cases that can be something that, that works out. And then finally, I think a very interesting application of Oblivious Prf, which will be looked into in more detail in some of Benny's talks, is private set intersection. So the first uses of this type of OPRF construction for PSI were a slightly different construction based on OT extension instead of vector Ole. And these are this KKRT paper from 2016, which reduced the use of public key cryptography in PSI protocols by relying on this OT extension preprocessing and obtaining reasonably low communication for the overall protocol. And then a more recent approach is to combine the vector Ole-based OPRF construction with some kind of polynomial-based encoding of the set inputs from the two parties. This actually leads to a really simple PSI protocol with essentially optimal communication. So in the protocol, the two parties just have to run one instance of vector Ole and then communicate an amount of information exactly proportional to the input size. It's very simple and natural protocol, and it's kind of described in a slightly obfuscated way in this paper from last year from Crypto, but hopefully there's enough information to decode that and discover it if you want to learn about it yourself. Okay, so that's the main part of the applications I want to talk about. Maybe we can pause for a second in case there are any questions.
There are no questions so far. You can go ahead.
Okay, thank you. Right. So in the second half of the talk, I'm going to look at some basic constructions of vector Ole. So as I said, these are not the silent constructions which will be covered in tomorrow's and Wednesday's talks. These are instead slightly more interactive ones. But importantly, even though these constructions are in some sense worse in terms of communication, I still think they're useful. They're important building blocks, since when you have these silent constructions based on pseudorandom correlation generators, they still require some kind of seed vector Oles to bootstrap them and maintain the protocol overall. So on this slide, I've got this taxonomy of, I guess, three main categories of vector Ole protocols. The bottom are the silent ones, which are largely based on the learning parity with noise assumption. And then the two I'm going to talk about right now, which are building vector Ole from Oblivious Transfer or building it from different types of homomorphic encryption. So there also are other approaches. For instance, you can build Ole or vector Ole from homomorphic secret sharing, but I'm not going to discuss that today. Okay, so how to build Ole from Oblivious Transfer. So this goes back to a protocol for secure two-party RSA key generation by Gilboa from 1999, which is essentially viewing Ole as a secret shared multiplication functionality, which is essentially part of what you want to compute when you generate an RSA public key. So Alice and Bob have these inputs, X, A, and B, and they want to compute AX plus B for Alice. So the first step is Alice will bit decompose her inputs into bits XI. This is a kind of natural thing when we want to do OT, where Alice is now going to play the receiver and use these as choice bits to the OT functionality. And Bob is going to do a similar kind of decomposition for its input BI, but instead of decomposing it into bits, he's going to sample random field elements, BI, which sum up to the correct value B when multiplying by these powers of 2. So this is kind of like sampling a secret sharing of B in this special form, such that it gives the right thing. But remember here, if B is random, as it often is when we want to use Ole, then Bob can actually just sample all these BIs independently as random ZQ elements. Okay, so then the parties will run a batch of Oblivious transfers. So in the first one, Alice inputs her choice bit X1, and Bob inputs the two messages, BI and BI plus A. Sorry, B1, that should be B1 plus A. We repeat this log Q times for each of the bits of X. Bob will always input this BI and BI plus A for the same A each time. So finally, Alice will output Y, which is this sum of the YIs combined with powers of 2, the same way as before. So we look at the outputs of each of these OTs. You can see that each YI is equal to either BI or BI plus A. So this is actually BI plus A times XI for Alice's choice bit XI, which is either 0 or 1. So then looking at Alice's final output, when we sum these together, we also get that this is equal to B plus A times X. So this is a very simple and I guess quite natural way of building, doing secret shared multiplication from Oblivious Transfer. Of course, if you want to extend this to build a vector Ole, then you have to repeat this n times, where n is the length of the vector. And there are a few optimizations you can do in this case. For instance, in vector Ole, remember Alice's input X is fixed for each of the multiplications. So that means when you translate it to the OT-based protocol, Alice's choice bits Xi are always going to be the same for each of these parallel invocations. So you can optimize the OT protocols based on that slightly and obtain some savings. So to summarize this basic protocol, it's perfectly secure, assuming we have an ideal OT functionality. And then to obtain each output of this secret shared product, we require this log Q calls to OT, where the inputs of the sender, at least, are these m-bit strings or ZQ elements. And so while if we rely on OT extension techniques, we can do this quite cheaply in terms of computation, at least, so we don't need to rely on a lot of public key crypto. This does have quite high communication costs. So we do m of these OTs on m-bit strings, so that's already at least m squared bits just for communicating the inputs, on top of whatever else we need to do the OT. This is essentially a quadratic blowup in the field size for doing a single OLE. Then another thing I want to talk about is active security. So what happens if we have active adversaries in this protocol who might misbehave and do something different? So firstly, if we look at the case when Alice is corrupt, note that all she's doing is inputting these bits xi into OT. So if she inputs a different bit into OT, as long as the OT protocol is actively secure, this is just changing an input. It's an input substitution. This is perfectly allowed by the ideal model with active security, so that's not a problem. The more challenging case is when Bob is corrupted. So here, remember, Bob's supposed to input this fixed difference bi plus a into the ith OT. And what happens if Bob uses some a prime in one of these executions? So here, if we do it in the first OT, then the output by Alice at the end when computing y will have this additive error depending on the difference a prime minus a multiplied with the bit x1. So this is something we have to try to prevent and make sure that Bob can't cheat by inputting different values and breaking correctness. So one natural thing we might want to try is just do some correctness check on the outputs of the OLE, or vector OLE in this case. So this is, I guess, kind of following the spirit of Henry's talk yesterday about secure sketches for verifying properties on secret shared data. I think whenever you want to build an actively secure protocol, one of the first things to try to think about is, well, firstly, looking at what goes wrong when the parties are corrupted. And then secondly, just seeing if there's some cheap way of verifying correctness without having to throw on expensive techniques like zero-knowledge proofs and things on top of that. So in this case, we just want to check that if we have a vector OLE, then all of these outputs satisfy this relation. yi is aix plus bi. A simple way to do this is have Alice send some random challenges over to Bob, so random field elements, and then Bob will use these to define some linear combinations of its inputs ai and bi, and send back this response a star b star over to Alice. Alice can then define the corresponding linear combination to the sum of the challenges times by her yi's, and then check that the OLE relation holds on these linearly combined values. So because OLEs are linear and we're just taking linear combinations, we get the same relation on the final outputs. Y star is a star times x plus b star. So there's one kind of obvious problem with this approach, which is when Bob's sending these a star and b star values, this is implicitly revealing some extra information about Bob's inputs. This is revealing a public linear function on the inputs, and we can't be having that. So we have to tweak this slightly by adding an extra mask to a star and b star. So we can do this by just extending the length of the original vector OLE to n+1 and padding these as we go along. And Alice will add the same padding to y star before doing the check, and that should fix this problem. So intuitively, the reason why this check should hopefully guarantee correctness is that to pass the check when some value yi was incorrect, because, say, Bob cheated in the protocol, then Bob has to essentially predict what the corresponding random challenge was in advance so that it will be canceled out by the right thing during this check. And the intuition here is that when these random challenges are chosen from a large enough field, this will succeed on with probability 1 over the field size. However, for this case, this unfortunately doesn't quite get us what we want. And the reason goes back to the exact kinds of errors that Bob can introduce on when he inputs some inconsistent input to the OT. So remember, we have this additive error, a prime minus a times x1. Of course, this error actually depends on Alice's secret input, x1. So if x1 is 0, then there'll be no error. And otherwise, there'll be this error chosen by Bob, essentially. So this is exactly a selective failure attack, which means that just based on the result of whether the correctness check passes or not, the corrupt Bob can learn one bit of Alice's input. This is something we may want to deal with. So one solution is actually just to not deal with this, relax the vector OLE functionality by allowing a small amount of leakage on the input X from Alice. So you can kind of model this by allowing the corrupt Bob to choose some guesses on X. And if the guess is successful, Bob learns this fact. If the guess is incorrect, then the protocol will abort. So this is essentially, on average, kind of 1-bit leakage on Alice's X. And it turns out for a lot of applications, this doesn't really matter, and you can just proceed with this small amount of leakage. And if you do want to get rid of it, if, for instance, X is protecting something really sensitive, then you can do some kind of privacy amplification by repeating the protocol a few times and then randomly combining different instances to ensure there's enough entropy in these X values, even after a bit of leakage. And this was something used in the mascot protocol for generating multiplication triples using Oblivious Transfer. So I should say that in mascot, at least in KOS 16, they're not explicitly building either OLE or vector OLE. They're directly building multi-party multiplication triples, but the techniques in there are kind of implicitly building OLEs on the way. And if you want to pull that out and use it to define a separate OLE protocol, then you could do. Okay, so to summarize, if we just want the passively secure protocol for vector OLE or OLE, then we have this very simple protocol with lightweight computation. If we make use of fast OT extension techniques, with this main drawback that the communication cost is now quadratic in the field length, which can introduce a lot of overhead in certain applications. And for the case of vector OLE, at least we can get active security very cheaply by doing this simple linear combination check. And if we tolerate a small amount of leakage on Alice's input, we don't need anything more. And it's essentially active security for free. So that's very nice. It's a simple protocol. And if you don't care about a bit of extra communication, it should be enough for your needs. Okay, so a different approach is to build vector OLE from homomorphic encryption. This will have different trade-offs to the OT-based approach. The main goal here, I guess, is to reduce the amount of communication and avoid this quadratic overhead. So here we're going to use a linearly homomorphic encryption, which operates over vectors of messages. So we have a public key encryption scheme with the usual algorithms, where the plaintext space is now vectors over ZP. We want this linear homomorphic property where, given some ciphertext, okay, so here I'll be using this box notation for encrypted messages. So given some ciphertext encrypting a message A, and a ciphertext encrypting message B, we can add these two things together homomorphically. We can also multiply by a constant. When we multiply by a constant, this could be a scalar or it could be a vector over ZP. And in the case of it being a vector, we now do component-wise multiplication of C times A after we decrypt, so that we get the right thing with this SIMD-style operation on encrypted vectors. So how can you build this kind of homomorphic encryption? Well, there are many different ways of building homomorphic encryption. The classic approach is the Palier encryption scheme, which doesn't actually encrypt vectors, it just encrypts scalars, but you can always just encrypt one element at a time to get a vector homomorphic encryption scheme. But the main drawback of Palier is that the plaintext space is now this ring Z modulo n, where n is an RSA modulus, so which obviously has to be very large and maybe a bit restrictive for your application. There'll be more about Palier and related techniques for building vector OLE from this in my talk on Wednesday. So another way of building homomorphic encryption might be to use the DDH assumption, the decisional Diffie-Hellman. So if you use classic Elgamal encryption, where you encrypt the message in the exponent of G, and then this becomes additively homomorphic. The only catch is that now to be able to decrypt, you have to solve the discrete logarithm problem. So this only works if your plaintext space has polynomial size. one nice way to resolve this issue is to work with class groups, where you can then support plaintext modulo P for large primes P. But finally, the actual main example I have in mind for this talk is using a lattice-based encryption scheme. So most efficient schemes from lattices are typically based on the ring learning with errors assumption over polynomial rings, where these schemes actually natively encrypt vectors expressed as polynomials. So we can directly encrypt a vector over ZP and do this component-wise addition and multiplication in a batch on a single ciphertext. Okay, so we can very naively build vector Ole from linearly homomorphic encryption by just having Alice take as input X, which is the scalar in ZP, encrypting it, and sending over the ciphertext and public key to Bob. So here, if the encryption scheme operates on vectors, you can just imagine Alice packing X into every component of the vector in the same way. So Bob will just apply this linear function based on his vectors A and B to compute a new ciphertext and send this back to Alice, who decrypts the result. Okay, so this is all very simple. It's a classic protocol. But I think it's helpful to think about what it actually takes for this protocol to be secure. So kind of obviously from Alice's side, if Bob is corrupt, then we want this encryption scheme to be secure. So if we have CPA security, then the encryption of X should hide X. And secondly, on Bob's side, if Alice is corrupt, we want the ciphertext Y to completely hide Bob's inputs A and B. And this actually isn't guaranteed by CPA security. This is a stronger property called circuit privacy, which says that after doing some homomorphic evaluation on a ciphertext, if I know the secret key and I've seen the ciphertext, then I cannot distinguish the actual function which was applied on the original ciphertext. So we have this property, then we get a secure protocol for a corrupt Bob. But unfortunately, when we're using lattice-based encryption schemes, circuit privacy is a bit of a problem. So for instance, in ring LWE-based encryption, we often have this like noisy structure of a ciphertext, where in your ciphertext, so firstly you have to scramble by masking with some function of the secret key. But if you take that away, then what you have is the message, which is encoded in, say, the upper bits of the ciphertext, and then it's partially hidden by some noise component of the ciphertext, which is in the lower order parts of the ciphertext, which are some integers modulo Q. So now when we apply a linear function to a ciphertext, the way we do this homomorphism is essentially applying the same linear function on the ciphertext elements as you would on the plaintext. We now get this different noise term, which depends on the secret inputs A and B chosen by Bob. So when Alice decrypts the ciphertext and recovers the noise to remove it, she will then have this leakage on the inputs A and B, which we want to hide. And the classic solution to this is to do something called noise flooding or noise drowning, where when Bob computes this linear function, he'll sample a large amount of extra noise, add this to the ciphertext before sending it over. But if we want this to statistically mask the original noise A times E plus B, then we need this extra noise sampled by Bob to be really, really big. It has to be essentially 2 to the security parameter times larger than the original noise in the ciphertext. So doing this requires larger ciphertext parameters. It increases the parameters of your lattice-based encryption scheme and makes everything much, much worse. So I want to mention there's a really nice technique which was presented by Vinod Vaikunthanathan at a workshop as part of Crypto last year. There is a video online where you can remove this noise flooding using something called gentle noise flooding, where instead of adding a very, very large amount of noise, you add just a small amount of noise and then essentially allow a small amount of leakage on some of these coordinates in the ciphertext. The way you work around that is then instead of encrypting the original message, you'll encrypt a T out of N secret sharing of the message. So that when Alice decrypts, if by some chance when this this noise doesn't map things properly, she learns a few coordinates of the original messages, then because these messages are just secret shares, it doesn't matter as long as she doesn't learn too many. So that's a nice technique for working around this, which allows you to work with much smaller ciphertexts and reduce the bandwidth and computation overheads from the naive method. Okay, so the second thing I want to talk about for linearly homomorphic encryption is how we can add active security to this. So again, it's instructive to think about what can go wrong. Is there some obvious attack that can break things? Well, in this case, not really. I mean, you can always have Alice and Bob send some kind of garbage ciphertext and then violate correctness, but it's actually quite hard to figure out how to do this in some way that leads to some leakage of sensitive information. Of course, that doesn't mean that nothing can actually go wrong. So we can try to say, okay, let's run this nice linear correctness check we use for vector Ole in the OT-based protocol and try to just verify things are correct. It's not obvious that there's any kind of selective failure attack, but we do get some kind of weird error in the outputs that has some dependence on the ciphertext noise, potentially the secret key used in the encryption scheme, and can cause things to fail in strange ways that are kind of hard to analyze. So it would be really nice to show that, okay, if we just do this, then we're all fine, there's no problems. But it's kind of challenging to prove that this was enough. So the way we actually add active security to these protocols is to go to the slightly less satisfying solution where we add zero-knowledge proofs. So for Alice, we want to prove that the ciphertext is correctly well-formed, which is a kind of proof of plaintext knowledge. And this guarantees that in the simulation, then the simulator can also extract the plaintext, which is needed for malicious security. And then for Bob, we want to prove that Bob applies this multiplication function to the ciphertext in the correct way. So this is for a zero-knowledge proof of correct multiplication. And doing these proofs for lattice-based encryption schemes is unfortunately kind of tricky, essentially because of the noise, which you don't have in classic number theoretic assumptions. You have to work a bit harder. So for the proof of plaintext knowledge, there's a very simple and naive Sigma protocol with just a 1-bit challenge. So this gets soundness a half, which then you have to repeat security parameter times, which obviously is undesirable. But there are many papers that look at optimizations to this approach. You can have slightly larger challenge spaces. You can amortize it when we want to prove knowledge of a large batch of ciphertext at once. But all of these are still kind of computationally expensive. They sometimes need larger parameters or only work on very large batches of vector Ole instances and add quite a bit of overhead compared with just a simple passive protocol. And then things are actually even worse when you look at this proof of correct multiplication. This is much harder to amortize compared with the proof of plaintext knowledge and adds a lot of overhead there. However, there is this nice technique from the Overdrive paper used for triple generation for the speech protocol, which essentially uses a kind of vector Ole-like protocol, somewhat similar to what I described, where we have a proof of plaintext knowledge, but it just then does some lightweight consistency check instead of adding these proofs of correct multiplication. And this can be proven secure if you add some extra assumption, which is sometimes called linear-only encryption, which is saying that essentially the only thing a corrupt Bob can do when it sends back a ciphertext to Alice is apply some linear function to the ciphertext or send some garbage ciphertext, which will always decrypt to an invalid plaintext, which is either invalid or independent of the original message. And this is kind of a strong assumption. It's been used in some lattice-based snark constructions, but it seems to be plausible. So there's one way of making things more efficient. Okay, so that's coming to the end of what I wanted to present for Ole and vector Ole. So I'll just conclude a little. So have you seen these two things are kind of core building blocks in all kinds of secure computation tasks. We can use them to generate correlated randomness of many different forms, multiplication triples, for matrix triples, as well as more special purpose applications like oblivious pseudo-random functions, which are a really important building block for private set intersection. The next talk will look into much more detail on a specific application to efficient zero-knowledge protocols from Vector Ole. And we looked at these non-silent protocols, so the classic protocols based on Oblivious Transfer and linearly homomorphic encryption. And even if these silent protocols, which we'll talk about in the coming days, are in many cases faster and perhaps preferable, I think the non-silent ones are still actually very important. Firstly, they're based on different assumptions, which may be more standard. And secondly, as I mentioned, these silent protocols always need some kind of setup phase to bootstrap them and obtain the silent benefits, which obviously has to be done with some kind of interactive protocol where we need this base Ole or vector Ole primitive. So it's still an important building block to look at, and there's still a few open questions, especially when it comes to doing active security with ring LWE-based encryption schemes. These zero-knowledge proofs are kind of a bottleneck and would be really nice to either improve or avoid. Okay, so that's about all I wanted to cover. So I'll be happy to take any questions if there's anything on Slack.
Yes, there are a few questions. So the first one is when you refer to silent Oles, what does silent mean here?
Yes, so I guess I didn't really explain that. It'll be covered more tomorrow, but silent essentially means that you have this interactive setup protocol which has very small amount of communication and just outputs a small kind of seed, which can then be non-interactively expanded to produce a large quantity of vector Oles or OLEs. So it's split into two phases, this kind of small interaction phase and then this silent expansion into a large amount of correlated randomness.
Okay. Also, when you do the jungle flooding, what's the advantage of using T out of N sharing instead of using just using an N out of N sharing?
Right. So I think for that one, it's not my work, but you need to use a kind of T out of N for some less than full threshold T, because you need to be able to, you kind of tolerate up to N minus T leaked coordinates in the ciphertext. And intuitively, each coordinate might leak with some constant probability, say probability of half, which means in the worst case, like up to half of these coordinates might be leaked. But I know, but then you need a smaller threshold so you can also reconstruct the original message, despite this leakage.
And then with respect to applications, there's a question if we can use vector Oles to construct protocols that can obliviously return shares of a value that is computed in a distributed way in the multi-party setting.
Okay, so I'm not sure I entirely follow the question, but is it perhaps talking about a kind of distributed secret shared version of vector Ole?
I think so. So the question says that it is in the multi-party setting with more than a single receiver where the values are computed distributedly and you want to obliviously return the shares.
Yes, okay. So imagining it's like a vector Ole where all of the, say, instead of X known to a single receiver, it's distributed across multiple receivers. And you have these kind of secret shared outputs of the vector Ole. So that's what you're looking at, then yes, that's something you can build, essentially from pairwise instances of vector Ole across the parties.
Okay. And the last question is the overdrive technique, the random linear combination check, an alternative to zero knowledge in RLWE?
So that's a good question. I don't know. It seems like you probably need something more. If you do just this check, I think it's very hard to actually prove that the ciphertext was well formed in the first place. But this kind of check is essentially very similar to the zero knowledge proofs that happen already. It's just they have to essentially do some more work to be able to prove things are well formed and extract the inputs. But it could be that something very close to this can work out.
That's all of the questions we have.
Great. Thanks very much.
Thank you very much, Peter. We're going to take a break, a lunch break till 2 o'clock. Resume then with your second talk for today. Thank you very much, everyone.
So, hi everyone, and welcome to the afternoon session of today. And Peter Scholl will continue his previous lecture in OLE, and he'll be talking about zero knowledge from vector OLE. And Peter, the stage is yours.
Thanks, Benny. Welcome back, everyone. So yeah, in this talk, I'm going to dive deeper into one specific application of vector OLE, which is building efficient zero-knowledge protocols that can scale to handle very large and complex statements that you want to prove things about. Okay, so this is the overview from the previous talk with all of the connected talks as part of this workshop. And this is now the second talk on volley before we have the PCG parts in the next couple of days. So what's the setting we're in? So we want zero knowledge for circuit satisfiability. That's what I'm going to focus on today. So we have some arithmetic circuit defined over a finite field, which consists of addition and multiplication gates in this field. And the prover knows some witness W such that the circuit evaluates to give 0 on input W. So the prover and verifier will run some possibly interactive protocol where at the end of the protocol, the verifier should be convinced that this statement is true. So the usual properties we want for zero knowledge, of course, completeness, that this protocol is correct if the prover is honest and the statement is true. And secondly, soundness, which means that if the prover is malicious, then it cannot convince the verifier that a false statement is true. And thirdly, of course, zero knowledge, which means that the verifier learns nothing about the witness known to the prover beyond the fact that this statement is true. And in this talk, all the protocols I'll talk about are actually also proofs of knowledge, which means that as well as proving that this circuit is satisfied, we also prove that the prover actually knows this witness W in the sense that we can extract it in a simulation. Okay, so within the topic of zero knowledge, there are many different protocols with lots of different properties. I'm not going to have time to talk about all of the different types of protocols and things there are today. But here it's just a list of what I think are some of the key properties that define and characterize zero knowledge protocols. So first off, you can have the runtime of either the prover and the verifier. Obviously, the prover has to evaluate the circuit, but may have some additional overhead on top of this, whereas the verifier's running time could be constant, or it could be also linear in the circuit size. And then we have the proof size, or the amount of communication sent over the network. Next, also the memory footprint can be an important concern. So this is normally focused on the memory of the prover, so whether there is a lot of extra overhead compared with evaluating the circuit in the clear. We can have interactive proofs and non-interactive proofs. And finally, we can consider proofs that are publicly verifiable to anyone who observes the transcript, or only with a designated verifier. So the verifier has some private randomness, which is used to check the proof. And the types of properties that we're going to focus on in this talk, or more specifically, the goal we want is to be able to support very large and complex statements with as low computation and memory overhead as possible, especially when it comes to the prover creating this proof. So in particular, the runtime of the prover, and I guess also the verifier, is going to be roughly proportional to the cost of evaluating the circuit in the clear. Part of the motivation for this is actually being driven by this DARPA CIV program, which is a research program launched last year by the US government, where they're encouraging people to look into these types of proof systems. I think partly as a research in a slightly different area to a lot of the current focus on zero knowledge proofs, which is in this succinct and publicly verifiable setting of interest mainly to blockchain applications. But there are actually many other interesting applications where you don't need these kind of things. You might be okay with a designated verifier. You might be happy with some interaction, and they could be useful things you want to prove. So a couple of examples related to proving properties about complex programs and pieces of software. So consider I'm some software provider, and I've given you an executable for a program. and I want to maybe provide a proof that this program satisfies some security property. So maybe it doesn't leak or do any kind of computation it shouldn't do on some private inputs. So on the other hand, I could have a proof that I actually know and exploit a security vulnerability in a piece of software. So if I'm a security researcher, this could be something that can help me to contribute towards a bug bounty program. So I can disclose a vulnerability or the existence of a vulnerability without having to actually give up the details of that and risk it falling into the wrong hands. And if you just try to think about proving any of these kinds of things, then obviously for realistic pieces of software, these are going to be hugely complicated statements. I think if you define them reasonably, you can actually come up with NP statements for this kind of thing, but the compile this down to a circuit or even a set of arithmetic constraints on the program variables is going to have a massive blow up on the size of the program. So we really need the proof system to be able to scale to handle this kind of statement. And so in the ZK from Volley approach, we will aim to achieve this while obtaining this relaxation, or I guess less desirable constraint that the proof size is not going to be linear. So the amount of communication is linear. In some cases, you can work around that, but not always. And we're also in the designated verify setting, where we may also have some interaction with the verifier. Okay, and so with that, a quick overview for the rest of the talk is I'll start by introducing information theoretic maps and how you can build these from Volley, and then show how we use it as a building block to build an efficient zero-knowledge proof system, which I'll mainly show in the form of this mac and cheese system, which is a paper from Crypto last year, as well as discussing a few other related protocols. And then I'll talk about 3 distinct extensions of this type of protocol, which you can look at. Firstly, a variant where you can make the proofs non-interactive and also be able to support streaming. So that's a kind of constant amount of memory from the prover as it streams the proof. And then secondly, I'll discuss an optimization where we reduce communication for proofs of disjunctive statements. So when you have several statements and you want to prove that at least one of them is satisfied. And finally, I'll talk about a new work called A to B, where we look at doing arithmetic and binary conversions between different representations of data to, again, improve efficiency. Okay, so before I start the technical stuff, any questions?
No.
Okay, great. So last talk, we saw a lot about Volley. And I briefly mentioned that we can get informational theoretic max from Volley. And actually, it's even stronger than that. You can view an instance of Volley on random inputs as an information theoretic mac. So here we have the functionality, which compared with the last talk, I've actually swapped the role of the sender and receiver around. So now the receiver is Bob on the right, who will play the role of the verifier in the zero-knowledge proof. So Bob has this scalar, which is now called delta, which is always going to be randomly sampled by the Volley functionality. And additionally, this other random output called ki for each of the I components of this vector. Whereas Alice has a chosen input, which is going to be this scalar AI, and then the other output, which is what I call the mac, which is mi equals a ki plus ai times delta. Okay, so this is a slightly different way of writing it compared with the previous talk, but I think it's easy to see that these things are actually equivalent. Because by writing it this way, we're viewing the mac, or the output of Alice, this value mi, as a mac on her input ai, where the corresponding mac key is simply the pair delta ki owned by Bob. So if you recall the Oblivious Prf example from the previous talk, then this key delta ki is actually also the same as the OPRF key used there. But here we're not going to hash anything. We don't need a pseudo-random function. This already is our max key. So now if you imagine Alice wants to send the value AI over to Bob at some point and verify that this is correct by sending the mac, Bob can simply check the mac relation using its key, ki, and delta, and verify that this holds. So why is this secure? Well, suppose Alice tries to open to a different value AI, say introduces some error E. Now, if we look at what happens if Alice has to pass this MAC check. So if she can come up with a different MAC, say M prime, which satisfies the MAC relation. So M prime is K plus A prime times delta for the A prime she sent, then we can subtract this from the original MAC MI and obtain this relation so that M prime minus MI now divided by this error E, which we know should be non-zero, gives us the MAC key delta. So if Alice could come up with any forgery for this MAC, then she must have guessed this MAC key delta. So as long as this finite field FQ is chosen to be large enough, then this succeeds only with probability 1 over Q, which can be negligible. Okay, so this is how you can get a large batch of MACs from a single long instance of vector Ole, where remember this scalar plays the role of this MAC key delta, fixed and known to Bo. So the way we'll view this in zero-knowledge schemas is by using these MACs as a kind of commitment to the messages known to Alice. So I'll use this square brackets notation again, this time to denote the set of MACs and keys held by the two parties, as well as the message AI. So I've left out delta here because that's fixed and the same for each of these values in a box. Okay, so the first thing we can notice is that these MACs are linearly homomorphic. So if we take MACs on A and MACs on B and add up the corresponding key, MAC, and values, then we get a valid MAC on A plus B. And similarly, we can define addition by a constant, but now we have to do it a little bit differently. So Bob, the holder of the keys, will now adjust his key K by adding C times delta. And this will turn the MACs into a valid MAC on A plus C. Okay, and one thing you might be thinking is, okay, so the probability of Alice being able to forge this was 1 over Q. But what happens if we want to use a smaller field, say F2 instead of a large field? Say if we want to do zero-knowledge proofs for binary circuits. So there is a way to work around this using a variant of vector Ole, which we sometimes call subfield vector Ole. So this is kind of like a batch of vector Oles on a small field. So where the messages A are defined in the small field, say F2 here, and then the MACs and the MAC keys are all defined over the larger field, of which the small field is a subfield. So here they're all in F2 to the K, and then we have the same relation, M is K plus A times delta in F2 to the K. And so since the MAC key delta is chosen from the large field, we have now an arbitrarily small cheating probability, even when the messages are small. Okay, so with that, I want to move on to the type of zero-knowledge protocols which we're going to be building, which fall into some loose family of commit and prove type protocols, where we use these MACs to build commitments to inputs, maybe some intermediate values, and then we'll run some auxiliary protocols for proving properties about these committed values. And the way I want to describe this is using a very specific instruction set, which you can use to then express all kinds of commit and prove protocols, including all the ones I will discuss, and kind of restricting it to this special instruction set allows some things to become a bit easier and helps you when applying some transformations I'll talk about later. Okay, so instructions are to commit to some value X known to the prover, outputting a commitment. Then we can open a commitment so that X gets known to the verifier. And then finally, we can do an assert zero statement, which proves to the verifier that all of these commitments that are input equal 0. Okay. And now the way we build these instructions using vector Ole is committing, we first will naturally take a next element of our random vector Ole, which will maybe come from some preprocessing phase or silent vector Ole protocol. And the prover will de-randomize this by sending this correction value X minus R, which can then be adjusted using the linear property of the commitment. Okay, and then to open, the prover will first send X, and then what we won't do is have the prover send the MAC. Okay, we could just have the prover send the MAC, but instead we're going to call this assert 0 command on the value committed X minus X, which obviously should be a commitment to 0. There's a couple of reasons to do this, but one is that simply when we run assert 0, it's actually more efficient if we just run it on a batch of operations at once. So we take in a vector of commitments A1 up to AM, and then instead of sending all of the MACs, we can check a random linear combination of the MACs using the same technique for verifying vector OLE in the previous talk, where the verifier takes these random coefficients, chi1 up to chi-m, and then the prover sends a linear combination on all of the MACs. And because this was originally a commitment to 0, then the linear combination applied to the MACs should be equal to the linear combination applied to the ki keys known to the verifier. So the verifier can just check this relation and output yes or no. Okay, so with these 3 instructions, how can we build commit and proof style zero knowledge for circuits? So the general paradigm is that the prover will first commit to the witness. We have these input wires W1 to Wn, and then they'll evaluate the circuit and the gate-by-gate paradigm, similar to the GMW protocol for MPC, where any linear gate is now easy to do without interaction because the commitments are linear. The only thing we have to handle is multiplication gates. We have input commitments X and Y. So the prover will first have to commit to this value Z, where Z should be equal to XY. And then the parties will run a verification protocol to check that Z equals X times Y. And notice that unlike the case of MPC, like in GMW, where the number of rounds of interaction depends on the depth of the circuit, in this zero knowledge case, because the prover knows everything, then we can run all these multiplication gates in parallel, having the prover send the information for committing to the Z values all at once, and then at the end of the computation, run this verification protocol in a batch for checking all multiplications. So that gives you a constant round complexity instead of one that scales with the depth of the circuit for MPC. And then finally, to verify the circuit, we assert that the output wire is equal to 0. Okay, so in mac and cheese, we have a couple of different methods of verifying multiplications. I'll first mention a very simple one, which has a slightly higher amount of interaction. So for each of these products, X, Y, and Z, we want to check that these are consistent. So the prover will first commit to some auxiliary commitment, C, which is supposed to be A times Y for some random commitment A, which is also taken from a random vector OLE. Then the verifier sends a random challenge, which is just a random field element, to which the prover responds by opening E times X minus A, and then the parties together run this assert 0 statement to check that E times Z minus C minus D times Y is 0. Okay, so why should this work? Well, suppose that this assert 0 statement succeeds. So we can kind of rewrite this. If we substitute in the value of D, EX minus A, into the assert 0, then we get a term of minus C minus Y, and we also get this E times Z and E times XY terms, so that this equaling 0 actually implies that C minus AY equals E times Z minus XY. So if there's any error in Z, then this thing on the right-hand side should be non-zero, which means that the prover must have guessed the challenge E to be able to pass this check. And just like the Mac check example, this gets you soundness 1 of the field size. And the cost of this is just the prover sending 3 field elements, where one of them was for the Z element, which was committed previously during the circuit evaluation, and then these 2 extra elements for committing to C and opening D. There's also a random challenge from the verifier, but this can actually be batched with all the multiplications So it essentially amortizes to nothing. Okay. So one catch is that unlike with the simple case for max, there's no really easy, efficient way of extending this to work for small fields. You could repeat things security private times, but that would incur quite a high increase in efficiency, decrease in efficiency. But the second protocol we'll look at can also handle that. So the more fancy version of mac and cheese is to do a single batch verification of all of the products in the circuit at once. And the way for doing this is essentially the same as one of the protocols which were presented in Henry's talk from yesterday, which uses this paper on distributed zero knowledge from fully linear PCPs and fully linear IOPs. We had this method of using polynomials to check that a bunch of secret shared values were bits. And this technique doesn't have to apply to secret shared data. It can also apply to committed data, as long as we can do the linear homomorphism on the commitments. The technique is very general and can essentially be directly applied here. Of course, we don't want to prove that these things are bits. We want to prove that there is a multiplicative relation between them. But actually, the same protocol, or a very similar protocol, essentially works in this setting. And by using the interactive variant of that protocol, this has a logarithmic number of rounds, but really nicely, the communication overhead is also only logarithmic in the total number of multiplications being checked. So this amortizes really well to give us something with essentially no communication overhead beyond just committing to the ZIs in the first place. And we can also make this work over small fields without too much extra cost. So we have these two different protocols. We can compare them. So if we look at the total communication in the proof, at least ignoring lower order terms and the cost of generating the volley in the first place, then we have to commit to the witness, which is size of W. And then for the simple version, we have three field elements per multiplication, whereas the fancy version, we have just one field element plus this log factor in the circuit size. And then computation, actually both of these are linear in the circuit size. The first version is a little bit cheaper, it's simpler, but the constants in the second one are not too bad. There's only a small overhead in doing that, and it can be parallelized well, so it's something practical. And then finally, the round complexity. Of course, the first one just has this simple challenge response, which you can do in parallel for all multiplications, whereas the second one, we have this logarithmic blowup because we have to do this recursive proof. Okay, so that's the basic mac and cheese protocols. With those, you can do kind of simple and efficient zero knowledge where both the communication and computation are linear in the circuit size. But as you've seen, like, it's all really simple operations. We're just using these information theoretic macs. There's no fancy crypto going on. If we have the vector Ole, it's all really easy. But one thing we might want to do is support streaming. So this is where the prover wants to be able to evaluate some proof or generate some proof kind of on the fly whilst it's processing the program without having to store the entire program or the entire statement in memory. So if you imagine we're in one of these settings where we're proving some complex property about a piece of software, expressing that this is a circuit or a set of constraints is going to be very expensive, incur a large blowup. Now sometimes you might end up with billions or tens of billions of gates in the corresponding circuit. And just storing the max for all of these things translates into a memory footprint already of hundreds of gigabytes. Unless you're on some kind of supercomputer, this might be pretty impractical. So you're going to want to process this proof in a streaming manner where you don't have to keep it all stored in memory. So how can we do this for mac and cheese? Well, if we look at the two variants of the multiplication checks, unfortunately, they don't really work directly in a streaming manner. So firstly, the fancy approach is implicitly based on this batch verification of doing all of the multiplications at once. And then similarly, in the simple one, even though you can do each multiplication separately, for efficiency, we want to batch all these assert zero statements at the end of the program, which then requires maintaining all of them in memory until we get them. But there's a kind of very natural and simple way around this, which is, okay, what if we just reduce the batch size? You know, we can execute this on, say, 10,000 multiplication gates at once, store those in memory, and then move to the next chunk of the circuit. So this works, but it of course blows up the round complexity. You have to interact every time you do this. This might lead to a lot of rounds of interaction. So can we get the best of both of these worlds? Well, the answer is yes, we can. Actually, the way to do this is very simple. It's just to apply the Fiat-Shamir transformation. So we take the multi-round version of the protocol, where we run one of the two mac and cheese instances on some small batch size. For the simple version, it could even be a batch size of 1, for instance, where you're just checking each multiplication one at a time with a fresh random challenge, sequentially. But now this is a huge number of rounds of interaction, but we can squash this just by applying Fiat-Shamir and generating each random challenge as the hash of the previous transcript and messages which were sent by the prover. Now, one danger here is that in general, Fiat-Shamir only applies to constant round protocols, or perhaps logarithmic round. And if you want to apply this in general, then you have to be careful when analyzing the soundness. So in the worst case, the soundness of the resulting non-interactive protocol might degrade exponentially with the number of rounds you have. Thankfully, it turns out that these simple information theoretic protocols we're looking at actually satisfy this property called round-by-round soundness, which was introduced by a paper from Canetti et al. A couple of years ago, and used for analyzing the Fiat-Shamir transformation. And we show that by kind of defining a formal model for these commit and prove type protocols we're interested in, and an analogous round-by-round soundness property, any protocol that satisfies this property can be transformed to be non-interactive, where the resulting soundness error is something roughly proportional to the number of hash function queries, or random oracle queries made by the adversary, divided by the field size, or Q times the original soundness error of the protocol. What's really nice is there's no blow up by the number of rounds here. So we can apply this to any mac and cheese like protocol, however many the rounds are, and just make it non-interactive like this way. So using this for the streaming setting gives us a designated verifier, non-interactive zero knowledge proof, which is streamable. So constant memory for the prover if the original circuit can be evaluated with a constant amount of memory. Of course, this ignores the vector Ole preprocessing, assuming some trusted setup, or assuming you have a way of generating the vector Oles in the first place in this streaming manner. Okay, any questions at the moment?
Yeah, one question. Is there a relationship between streamable zero knowledge proofs and incrementally verifiable computation or recursive snarks?
Right. So I'm not sure if there is any relation there, because the streaming it's about streaming as you produce the proof, but it's not verifying, it's not kind of recursively verifying another proof. So there may be some connection, but at least I don't see a direct one. So I haven't looked into it closely.
Okay. Yeah, that's it.
Okay, great. Okay, so the second extension of these mac and cheese type protocols I want to look at is to applying or proving disjunctions in these commit and prove systems. So what's a disjunction? Well, if you have a set of several circuits, here we have, say, m subcircuits, which each compute values y1 up to ym. We compute a disjunction of these by just taking an OR of all of their outputs, which evaluates to 1 as long as one of them is true. Okay, so you might say, okay, well, we look at this. This is a circuit. We can apply mac and cheese to this and produce some proof. Well, it's okay, you can do that. So then the proof size is now going to be m times the maximum, the size of each of these subcircuits. An alternative strategy you might take is to actually look at this classic approach of doing all proofs by Kramer, Damgaard, and Schoenmaker from back in the 90s, which shows how you can take any Sigma protocol type zero knowledge proof and compile it into a proof of the disjunction of several such protocols. But also this transformation has a linear overhead in the number of disjunctions, and you end up with the same m times circuit size blowup for performing this proof. And we want to see if we can do better. So I'll say the inspiration here is from this stacked garbling line of work, which has been looking at doing disjunctive proofs for zero knowledge proofs, and also disjunctive circuits for garbling and two-party computation with this stacked garbling framework that has a line of several recent papers. And so we try to apply a, I guess, analogous technique to mac and cheese, getting something I like to think of as a stack and cheese. So the more mac and cheese, the better. So the goal is to communicate only the information proportional to the longest branch in each of these subcircuits we're doing this disjunction on. So why might this even be possible? Well, the key is to go back to this the set of 3 instructions we had in commit and prove protocols, where we commit, we open, and we assert 0. If you look at all of the mac and cheese proofs for verifying multiplications, then the way they use these instructions is that all of the messages which are being sent by the prover during this zero knowledge proof are just simply random field elements. So apart from this assert 0 call, which can be batched and postponed till the end, remember, the prover is just sending a bunch of random values of the y. Okay, so if you're looking at a proof of a single circuit, say C1 or C2, the verifier can't actually distinguish whatever it's getting sent is a proof corresponding to one circuit or the other. In any case, they're just uniformly random. So perhaps we can optimize this by having the prover only send the messages corresponding to the subcircuit which is actually correct. And then the verifier can take the messages and interpret them as it would for the case of it being C1 and circuit C2 in each case. And one of them will evaluate to true and the other one will evaluate to false. Of course, the problem here is that we need to somehow combine these subcircuit results together. We have to do an assert 0 statement to verify each branch, but we only want to do that on the correct branch without revealing which is the correct branch. The solution there is to actually apply this small all proof technique, so the CDS technique, where at the end of evaluating each of the branches, we do a kind of subproof to verify that at least one of these gives us the correct assert 0 statement on all the values we're interested in. Okay, so in a little more detail, let's suppose there are m subcircuits, C1 up to Cm, and in, say, index I, the prover knows some witness, which means that this evaluates to the right thing, so it's true. So the prover is just going to run the protocol for circuit Ci. Let's suppose these are all of the same length or same number of multiplications, at least. And then the verifier will send random challenges as required. And at the very end, so we get to this protocol where we have this assert 0 statement, which we want to use to verify that things are correct. So as if the verifier just takes the steps for each of the circuits C1 up to Cm and defines all the possible valid commitments, say Z1 up to Zm, where if we were doing circuit Ci, we'd want to verify that Zi is 0. Of course, for any index not equal to I, these are just going to be garbage commitments. They might not even be valid. No, sorry, they will be valid commitments, but they may not be 0. And then we just run this all proof on the committed values to show that there is at least one index satisfying Zi is 0. And although this OR proof is technically defined in terms of sigma protocols, it's essentially based on these nice linear properties with a random challenge from the verifier. So it applies directly to commitment-based MACs as well. Okay, so if you run this approach, then the communication, instead of being the sum of all of the circuit sizes, is now proportional to just the maximum of each of these branches, because we'll always have to pad to the maximum of the subcircuits just so that we don't leak anything about the size of the one which is being evaluated to true. And we additionally have this O of M overhead, which corresponds to the last part where we do an OR proof to show that at least one of these is 0. So this is up to a factor of M saving for large enough circuits compared with the naive approach. Okay, so a bit more about the general characteristics of this is that we show that this kind of transformation applies to any class of these commit and prove type protocols, which you can model with the instructions I described earlier, which can also be formally characterized as this linear interactive oracle proof, introduced by the paper where we used the, with the check, which we used for the fancy version of mac and cheese multiplication. And there is another recent work from last year, which has a similar kind of transformation, this time applied for general Sigma protocols. The Sigma protocol is just a zero-knowledge protocol with a public coin verifier. And this is a kind of slightly different technique. On the one hand, it's more general, but on the other hand, it's not this information theoretic transformation like what we do. It uses cryptographic tools, so it gets you something a bit different. In our case, we also show how you can extend this disjunctive proof to support threshold disjunctions. So you have M circuits and you want to prove at least K of them are satisfied. Well, you can do this with a communication K times the largest circuit plus this O of M factor. And lastly, so just for fun, because we really like doing this disjunction so much, we look at doing disjunctions inside disjunctions in this nested way, so you can have arbitrary layers of nesting, which is something you might well come across if you want to do proofs of realistic programs with lots of branching in. And also it actually allows you to apply this recursive step directly for doing this small OR proof at the end and reduce this O of M additive overhead to just logarithmic in M. Okay. And lastly, I want to talk a bit about zero knowledge from other Ole-based approaches that aren't mac and cheese. So I'll mention a couple of closely related works, in particular line point zero knowledge and Quicksilver, both from last year, where they do things a little bit differently to the way I use mac and cheese. So instead of working in this, I guess, abstract linear commitment paradigm where you don't really exploit any of the features of the vector Ole when doing your proof, they actually make some kind of non-black box usage of the macs so you can check things in a different way. And the idea is that if you actually look at these mac relations for a set of different committed values, then you can kind of have the prover just like multiply together two different macs on different values. And this gives you some kind of quadratic relation in the mac key, which you can actually exploit to be able to check a multiplicative relation on committed values more efficiently. So the core tool which both of these works get you, I think the Quicksilver approach is a little bit simpler, but it's essentially very heavily and closely related to the line point ZK method, is you can take three committed values, X, Y, and Z, with their max, and then the parties can locally use these to define a fourth value, commitment to C, where if this original input was a valid multiplication triple, then C is a valid mac, where C is known to the prover and the prover knows the mac. If Z is not equal to X times Y, then this is just going to be some garbage mac, which doesn't even verify. Okay, and the prover should not be able to come up with a mac in that case, which verifies except with negligible probability. So then this opens up this really nice way of checking a large batch of multiplications by just checking that this batch of C's you can produce is a batch of valid max. So you just take a big linear combination of these, open them all at the end. This is basically a constant communication overhead for verifying multiplications. So this is a super nice approach for doing multiplications, although it doesn't fully supersede the mac and cheese type approaches because of this non-black box use of vector Ole that it makes use of. So here's a quick comparison between a few different approaches of doing zero knowledge for circuits. So it's the two mac and cheese protocols, and then also compared with a different approach based on garbled circuits, this stacked garbling paper I mentioned earlier, which can also support disjunctions. But there, the communication cost for proving Boolean gates is at least the security parameter, because you have to send over this garbled ciphertext for every AND gate in the circuit. With mac and cheese, if you do a Boolean version, there's a variant of the simple protocol, which I did not talk about, which can reduce, which can get a cost of around 9 bits per AND gate, compared with 3 field elements for the arithmetic version. While in both cases of Boolean arithmetic, the fancy version of mac and cheese gets you this amortized cost of 1 field element per multiplication, which is also matched by the Quicksilver approach with this simple non-black box verification. And of course, making this non-black box use of vector Ole now means that Quicksilver doesn't quite fit into this paradigm where you have these abstract commitment instructions with commit, open, and assert 0, because it does something under the hood with the vector Ole's to do the multiplication. And that means it doesn't work with our disjunction approach. So what would be really nice to have is a way to do disjunctions with Quicksilver whilst preserving this simple multiplication check without having to go with the more expensive polynomial-based approach in mac and cheese. And in terms of computational efficiency, there's also some implementation numbers on this slide in terms of millions of multiplications per second. I think these are actually run on different machines, so don't take them too closely, but essentially it looks like Quicksilver is a bit faster than the competing fancy mac and cheese approach, which basically corresponds to having less computation, because this very simple check is a bit simpler than this recursive logarithmic round check, which also has more rounds of interaction. And I guess it's also maybe worth talking a little bit about other approaches to scalable zero knowledge. So there's all kinds of protocols you might want to talk about, like snarks and things. But I think the bottom line is that if you want something which has some constant memory overhead so that you can evaluate in this streaming fashion, then as far as I know, none of the practical snarks that are out there these days will get you this. Perhaps a more closely related technique is MPC in the head, which uses similar MPC type techniques to do proofs, but this time with public verifiability. But MPC in the head, to get this public verifiability, essentially always incurs a higher communication cost for the types of circuits we're interested in. One exception, of course, is the Ligero protocol, which has this square root of the circuit size complexity, but at the cost of higher computation. Okay, so that's the summary of all of these circuit-based protocols. Now, in the last part of the talk, I want to talk about another work in this family, which is about conversions between arithmetic and Boolean representations. So this is Appenzell to Brie, following in the cheesy line of names, which we often go for the papers in this project. So why would you want to do conversions in zero knowledge? Well, as I've talked about so far, the proof systems can support inputs over any finite field, but you cannot mix these. You can either do F2, or you can do FP for some other value of P. And depending on your problem, you might have more efficient circuits over different fields. So in the dream world, we would just take our program, and then at every step of the program, we'll be able to switch to the representation we want to do whatever operation is more efficient in that representation. So to illustrate this, you can look at some examples. Say if you're in a Boolean circuit and you want to do an integer multiplication, obviously this has a really large binary circuit representation with a lot of AND gates. As on the other hand, if you're in an arithmetic circuit and you want to do something like a comparison or truncation on your arithmetic value, then this is actually really expensive to emulate as a circuit of FP, because the corresponding function has very high degree as a polynomial over FP. These are the cases where you might want to switch between representations for more efficiency. So in a nutshell, our Appenzell-Tobrie protocol is a way of getting something like this, which allows you to start with your proof system over FP, say, to do some arithmetic part of a computation. You end up with some committed state, say some intermediate values, X, in your circuit. And then maybe you're at a point where you want to switch to a Boolean proof and run mac and cheese over F2 for a different part of the circuit. And A to B is just a proof gadget you can think of, which you can plug in and prove that these two representations are consistent. So the arithmetic value of X is equal to the bit decomposed version, which is given in F2. And our gadget can essentially do this kind of check for any fields. We have some mild constraint on the size of the prime related to the size of the actual data, which is working underneath. And the way we do this is inspired by a technique called extended doubly authenticated bits, which was first introduced in the context of MPC, and also used in another paper doing a similar thing for zero knowledge. Okay, so the basic idea to do this, this kind of conversion gadget is as follows. So suppose we have these two intermediate computations, like commitments over FP and corresponding commitments over F2. We want to prove these are consistent. So the proof is going to generate some auxiliary random data, which maybe comes from the preprocessing if you want to optimize things, where it commits to some random values, say a set of Ys, which are random field elements, and the corresponding bit representation of F2. But then for each of these Ys, we're going to simply open the sum of the input X plus some random challenge E multiplied by the Y. And we'll do this opening over both the arithmetic world. Okay, here this is simply a linear operation that's basically free. And also over the binary world. This is where things get a bit more tricky. So if we're doing this over a binary world, we don't really want to do a multiplication of some large finite field element times by some bit decomposed value Y. So we can choose the challenge to be 0 or 1, and we don't have to do any multiplication, it's just an addition. And of course, here we only get soundness a half, because we have to do a lot of repetitions to make this work, and we'll get a very expensive proof. But if we want to increase the soundness, then this gets expensive. So what we do is not exactly this, we apply some things on top of this to make things better. Essentially, the way to make that work is using cut and choose. So instead of checking every single conversion tuple directly with these randomly preprocessed things, we'll firstly take a large batch of conversion tuples which you want to check, and then shuffle these into random buckets, along with some auxiliary random check values which are used to verify them, and open some fraction of the random preprocessing to ensure that most of them are not incorrect, and then apply the same type of check within buckets. And what this means is when we apply this check here, we can essentially do the same type of operation where E is now binary, or even always fixed to 1 in this case, but we're doing this on a small kind of randomly permuted bucket for each of the X's we want to check. And now the bucket size can be as small as 3 in some cases, depending on your security parameter and the number of conversion tuples you want to check. So the cost of doing this verification is essentially the cost of verifying 3 binary addition circuits using your binary proof, which you can do using Quicksilver or mac and cheese as you like. So we have a few extensions to this basic approach. One thing we looked at is because you're doing these binary addition circuits with all of these buckets, and that's the kind of main cost, we looked at what happens if you don't perhaps fully verify each of these addition circuits. So maybe your verification of addition is allowed to be slightly faulty. And for instance, this can happen if you use like a more lightweight version of mac and cheese. You can consider where there's some probability that the prover can get away with an incorrect multiplication. And it turns out by incorporating some checks into the cut and choose procedure in the right way, you can make this work even with faulty addition circuits, which can, in some cases, get you a bit of improvement. And then furthermore, as an application to this, we show how to use these conversion protocols to directly verify truncations and comparison gates within circuits. So instead of just Boolean or arithmetic circuits, we can kind of incorporate these extra gadgets for doing a truncation or a comparison on an arithmetic value with a conversion type proof. Okay, and a final part of this is within this A to B paper, where we also actually look at conversions between F2 and FP, and also the integers mod 2 to the K, so Z2 to the K. As part of that, we also looked at, okay, what happens if you want to actually do mac and cheese mod 2 to the K? Because here things don't quite work out as you might hope. One solution, of course, is to emulate these operations over a binary circuit, but that's not very nice. You don't get free addition. Multiplication gets expensive. So the second solution we looked at is actually making mac and cheese work with some different kinds of multiplication checks. So the immediate challenge is the presence of zero divisors in this ring Z2 to the K. And a second problem is that when you actually look at the vector Ole protocol, existing protocols that are out there aren't quite designed for Z2 to the K, and in particular don't work for active security if you want to get that protocol. So we managed to solve the first problem by applying some techniques from the speeds 2K paradigm from multi-party computation over these types of rings. Essentially by lifting to some larger rings for doing max and multiplication checks, you can make these things work out despite the presence of zero divisors. Well, the second problem has not yet been solved. Okay, so wrapping up, in this talk, I hope you've seen that vector Ole, as well as being useful for all kinds of MPC stuff from the previous talk, it actually directly gives you information theoretic max, which are a really natural and simple way of doing zero knowledge proofs with low computational cost and good complexity for the prover, despite this high communication cost. As well as that, we can do this stacked OR proof technique to optimize disjunctive proofs in different settings. And finally, also do conversion gadgets between gates, between circuits of different representations, between binary, arithmetic, and even operations over rings like Z2 to the K. So a few open questions I'll quickly conclude with. So obviously the real kind of killer protocol to be able to get for this Ole paradigm will be something where you don't have to interact for every gate of the circuit. Okay, there are special cases like disjunctions and some other more structured kind of circuits where you can get this slightly sublinear, but it would be really nice to do better in general and get something like a succinct vector commitment from vector Ole. Don't know if that's possible, but maybe. And secondly, obviously, another limitation of this is that we're in this designated verify setting. Well, sometimes that might be what you want, or it might be okay for your application. It's also nice to have public verifiability sometimes. And there's a couple of recent works on ePrint, which look at a kind of in-between setting where you have multiple verifiers. So still not publicly verifiable, but you can prove something among a larger group of verifiers than just one. And finally, I think, especially in the space of conversions and support for Z2K, there's definitely room for making things more efficient, reducing communication costs, and so on for the protocols that I presented there. So that's all I have, and I'll be happy to take questions.
Yeah, one question is that is designated verifier inherent to these techniques? And do you think it's possible to get publicly verifiable zero knowledge proof using vector OLE?
Okay, well, I guess that's touching on the open question I just mentioned.
Yeah.
But to expand a bit, it kind of is inherent when you have these information theoretic MACs, right? The verifier knows the secret MAC key delta, which you really have to keep secret from the prover. So if you think about it, you can't really have any way of having the prover generate this MAC key on its own without relying on any private verifier, because as soon as it has some way of computing this MAC key, it will be able to cheat the proof. So it seems like a tricky barrier to overcome, but that doesn't mean it's not possible.
Okay, so last question is, which cheese is next?
Which cheese is next? So one of the ones on ePrint on this multi-verify setting has been called feta. The reason for that is, I think, slightly tenuous perhaps, but it's because when you take feta, you crumble it into many pieces onto a salad. So breaking up the single verifier into multiple verifiers.
Yeah, that's it. Thank you.
Okay, thanks.
Okay, thank you, Peter. Thanks for wonderful 2 talks. And we'll see you again later in the school. And, more talks. Okay, thank you, and thank you, everyone. And we will continue tomorrow.